Hello there, and welcome to Just About Earth, where curiosity gets cozy and science takes the scenic route to slumber. Tonight, we'll take a step back into one of the most fascinating moments in our planet's history. It was a time long before us, long before cities, long before our kind even existed. The Jurassic Period. You've probably heard the word many times, usually linked to movies full of towering dinosaurs, giant teeth, and thundering footsteps. But the truth is much richer, more detailed, and a lot stranger than what pop culture usually shows us. And together we'll move slowly into that world, not rushing, not forcing anything, just letting the story unfold the way landscapes unfold when you look out a train window and let the scenery drift by. Before we begin properly, let me turn toward you for a moment. Because these journeys are not just about the Earth millions of years ago, they're also about where you are right now. So tell me, in your own quiet mind, what time is it where you're listening? Is it late, with lights dimmed, the air a little cooler, maybe your body already ready to settle into rest? Or is it earlier in the day when things around you are still moving, but you've carved out this small pause just for yourself? Are you at home, maybe in bed, maybe on a couch, or are you somewhere else entirely, using headphones to carry you into another world for a while? However you've arrived here, it's just the right time. You've already made space for this moment, and that's all it takes to join me on this path. And if you find this kind of wandering exploration soothing, if you enjoy learning without pressure, without a rush, and without the sharp corners that science sometimes gets presented with, I'd be grateful if you tapped the like button, or maybe subscribed. It helps this little corner of calm reach others who might also be looking for a soft landing at the end of a long day. It keeps the path open for anyone else who wants to learn about the world, while letting their shoulders drop and their thoughts loosen at the same time. So now, let's begin to ease into the Jurassic. This was not just a backdrop for giant reptiles. It was a real place and time, stretching from about 201 million years ago to about 145 million years ago. Think about how much space that covers. All of human history fits into a tiny fragment of that span. Civilizations rising and falling, technologies invented and replaced, entire cultures leaving their mark and then vanishing. All of it would look like a flicker compared to the length of the Jurassic. Yet, despite that enormous gap of time, the Earth would not have felt completely alien to you if you stood there. The sun rose in the morning and set in the evening. The moon tugged at the oceans with tides that would have felt familiar, though a bit stronger because the moon sat closer than it does now. Clouds formed, rain fell, rivers carved valleys, and forest rose. You would recognise much, even as you noticed differences. The Jurassic was the middle act of the Mesozoic era, the so-called Age of Dinosaurs. But it's important to remember that it wasn't just about dinosaurs. That phrase, while convenient, hides how much else was happening. Plants were spreading and evolving. Oceans were alive with shapes that don't exist anymore. Continents were breaking apart slowly but surely, setting up the arrangement of land and sea that would eventually become the world you know. Volcanoes shaped mountains. Storms swept across wide open coasts. It was a time when the planet itself was restless, and life had to match that restlessness by adapting, changing, and growing. Imagine walking into that world. The first thing you'd notice is the warmth. This was a greenhouse Earth, warmer than today. There were no polar ice caps. Even high latitudes were more temperate than icy. The air held more moisture, making it heavier, more humid. You'd breathe it in and feel the difference, not uncomfortably, but noticeably. Around you would be forests, not of familiar oaks or maples, but of conifers, cycads, and ferns. Tall trees reached up with thick trunks, their needles forming green canopies. Beneath them, cycads with stout stems and crown-like tops stood in clusters. Ferns spread across the ground in wide mats, covering open spaces the way grasses cover fields today. But grasses didn't exist yet. The landscapes were green, but not in the same way your eyes are used to seeing. As you looked closer, movement would reveal itself. a branch shifting not because of wind but because something heavy brushed past, a tail swaying, long and powerful, a neck arching upward to pluck at leaves. Dinosaurs were here, yes, but not all of them were massive. Some were small, quick and nimble, darting between plants. And it wasn't just dinosaurs. Insects buzzed and crawled, some familiar in form, some strange. Early mammals, tiny and often hidden, crept through the undergrowth. Birds, or at least the first versions of them, flapped in the trees. Oceans not far away rippled with creatures that resembled reptiles but lived like fish. Plesiosaurs with long necks, ichthyosaurs with sleek dolphin-like bodies. It was a world of constant motion, filled with both giants and things so small you'd overlook them if you weren't paying attention. And that's the part that often gets lost. We think of the Jurassic as if it were a stage play, a parade of massive dinosaurs stomping across the floor. But it wasn't staged. It was alive. It was ecosystems that worked, with predators and prey, with plants and pollinators, with cycles of growth and decay, with daily struggles to eat, to reproduce, to survive storms, droughts, and volcanic eruptions. Every creature, large or small, was part of something bigger, and none of them thought of themselves as extraordinary. To them, life was just life. They didn't know they'd one day be turned into fossils, studied by strange descendants of mammals in far-off ages. They simply lived, the way creatures do now. It's strange but grounding to think of that. The dinosaurs you imagine, the ones you've seen in illustrations or museum halls, never knew they were dinosaurs. They were just animals. They woke, they ate, they searched, they fought, they slept. Their bodies were adapted to the conditions around them, and they lived inside those conditions the way we live inside ours, which means that while we can marvel at their size or their strangeness, we can also recognize something ordinary. Life, wherever it exists, is always trying to keep going. That's what makes the Jurassic not just a gallery of fossils, but a living story. The Earth itself was constantly shaping that story. The supercontinent Pangaea had begun to break apart. That process started in the Triassic, but by the Jurassic it was well underway. Imagine continents slowly drifting, oceans widening, coastlines stretching and shifting. What looks solid to us is never truly still on geological timescales. Back then, what is now the Atlantic Ocean was opening. Land masses were pulling apart. That meant new shorelines, new shallow seas, new habitats. Life had to spread into them, filling niches as quickly as they appeared. When you imagine those landscapes, don't picture them as static paintings. Picture them as moving, changing, filled with sound. The calls of animals echoed through forests. The splash of something large entering water broke the surface. Insects hummed in the background. Wind moved through the trees. Thunderstorms rolled across open expanses heavy with rain. Volcanoes rumbled, their slopes glowing faintly with a molten rock. It was a noisy, busy world. And here's the part that makes it almost comforting. As much as things have changed, as much as the species and landscapes were different, the rhythms weren't unfamiliar. Sunlight warmed the day, shadows lengthened toward evening, stars filled the sky at night, rivers ran, trees grew, storms passed. Those patterns are timeless. They've been here as long as Earth has had land and water and air. So while the Jurassic might seem impossibly far away, it also shares something deeply familiar with you. Now let's pause here for a moment, not to stop but to catch our breath as we continue, because this is just the beginning of the story of the Jurassic. We've set our feet in its soil, felt the warmth of its air, and noticed the outlines of its forests and oceans. But the details run deeper, and each one adds texture to the world we're slowly stepping into. When you step further into the Jurassic, the first thing worth doing is grounding yourself in what the planet actually looked like around 200 million years ago. We're used to seeing Earth as a map, with continents shaped like puzzle pieces that all fit neatly into familiar outlines. But the Jurassic Earth was not arranged the way we know it now. The land was still in the process of pulling itself apart after having spent millions of years as one colossal landmass, a supercontinent we call Pangaea. Picture it stretched across much of the globe, a huge expanse of connected land surrounded by a single enormous ocean. By the early Jurassic, cracks had already begun to open, slowly, steadily, separating what would one day become the continents we know today. The Atlantic Ocean was just starting to take shape, not yet the wide expanse it is now, more like a chain of newborn seas nudging their way between drifting pieces of crust. If you could hover above the planet in that age, the shapes would look familiar in some ways but very different in others. To the north, what would eventually become North America was beginning to pull away from Europe and Africa. To the south, what we now know as South America, Africa, Antarctica, India and Australia were still linked together in a block of land called Gondwana. That great southern mass stretched across wide latitudes, carrying deserts, forests and coastlines with it. The process of breaking apart didn't happen in a sudden crash. It unfolded slowly, over tens of millions of years, but the evidence was already written in the landscapes. Long cracks, called rift valleys, were opening. Volcanic activity was common along those rifts, pouring out basalt and reshaping local environments. Each pulse of lava left a new layer behind, hardening into the foundations of continents to come. For life on the ground, those changes didn't look like a world map shifting. They looked like new coastlines appearing, new rivers carving through valleys, mountains rising where the land had been flat before. Creatures adapted to those changes just as animals adapt today when landscapes alter, even if they didn't understand what was happening. To a sauropod moving across a forest, the drift of continents was invisible. To an early mammal hiding in the undergrowth, a rift valley might have seemed like nothing more than a canyon to avoid. But taken together, those changes were laying the groundwork for the planet, you know. The climate during this time was different from today as well. Because the continents were clustered together, the interiors of those large land masses often experienced extremes. Deserts spread across some regions, with temperatures swinging hot in the day and cold at night. Along the coasts and near the growing seas, humidity and warmth dominated. The poles, unlike today, weren't capped with thick sheets of ice. Instead, they were milder, supporting vegetation rather than frozen wastelands. Imagine a world where forests stretched almost everywhere, reaching into high latitudes, unbroken by polar ice. That was the Earth of the Jurassic. Atmospheric carbon dioxide levels were higher than modern levels, which helped trap more heat and kept the planet in a greenhouse state. That warmth didn't mean the planet was uniform. There were still regional variations. Some areas were drier, others wetter. Monsoon-like systems likely brought heavy seasonal rains to some parts of the continents. But the overall picture was a warmer, wetter Earth, one that supported vast amounts of vegetation. Forests grew dense and tall in many areas. Conifers dominated, much like they do today in places such as the Pacific Northwest, though the species were different. Towering relatives of today's redwoods and pines spread across wide ranges. Ferns carpeted the ground in thick mats, especially in humid zones. Cycads, with their thick trunks and stiff leaves, were common. Horsetails grew in wet ground, their hollow stalks reaching impressive heights compared to the small versions you might see today along riversides. Together, these plants built environments that could sustain large herbivores, and large herbivores were certainly present. But before thinking of the animals, it's worth pausing again on the scenery itself. Without grasses, the landscapes looked different than what we're used to. No open meadows, no wide grass plains. Instead, there were fern prairies, low mats of green covering open land where moisture allowed them. In drier areas, cycads and conifers dominated, standing apart with space between them, their crowns forming distinct shapes against the sky. Along riverbanks and floodplains, horsetails and ferns thrived, their stalks and fronds forming dense thickets. The effect was a patchwork of plant life, structured differently from modern ecosystems. Rivers and lakes dotted those landscapes. Some were seasonal, filling during rains and drying when the weather shifted. Others were permanent, fed by rainfall and underground springs. Lakes could be large, occupying rift valleys, their waters reflecting the forests around them. Along the shores, life gathered just as it does today. Small animals came to drink, predators followed, plants took root in the moist soil, and insects filled the air. Oceans, meanwhile, were beginning to host their own drama. The single great ocean that had surrounded Pangaea, called Pangaea, still stretched across much of the globe. But new seaways were appearing as Pangaea split. The Tethys Ocean, lying between the northern and southern land masses, was an especially important body of water. Warm, shallow and full of nutrients, it provided a cradle for marine life. Coral reefs expanded within it, building habitats for fish and invertebrates. Marine reptiles prowled those waters, hunting with speed and power. The oceans of the Jurassic were far from empty. They were as full of competition and survival as the land. The air itself was also different. Oxygen levels are thought to have been somewhat higher than today, though estimates vary. If you breathed it, you'd notice the humidity more than the oxygen. The combination of warmth, moisture and plant life gave the Jurassic atmosphere a richness, a thickness you'd feel on your skin as much as in your lungs. And it was filled with sound. Insects hummed, amphibians croaked in wetlands, dinosaurs called to each other across forests. The sky was not silent either. Pterosaurs, flying reptiles with wings stretched by long membranes, soared overhead. Their cries joined the chorus, creating a soundscape that would have felt alive from dawn to dusk. At night the stars appeared just as they do now, though shifted in their arrangement. The Milky Way stretched across the sky. Familiar constellations had not yet been named, but the same stars burned. The moon was closer, so it looked larger, and its pull on the tides was stronger. Nights along coastlines would have carried the rhythm of waves crashing under that bright lunar glow. Inland, the sounds of the forest carried into the dark. Predators moved more carefully. Prey stayed alert, and the cycle of survival continued even while much of the forest rested. It's easy to think of this scene as alien, but the more you let it settle in, the more it becomes familiar. Rivers, forests, storms, tides, animals searching for food, parents protecting young, creatures competing for survival. Those are patterns that still exist today. The species were different, the plants arranged differently, the continents placed in other configurations, but the principles of life remain the same. That's what makes picturing the Jurassic Earth possible. You don't have to stretch your imagination into something unrecognizable. You just have to shift the details. This was the stage onto which the great animals of the Jurassic walked. They were not separate from it. They were part of it. Their lives depended on the vegetation, the rivers, the coasts, the climates. They shaped those environments in return. The sauropods that ate from treetops pruned forests in ways that opened space for other plants. The predators that hunted kept populations in balance. The insects that pollinated and fed birds or early mammals linked the smallest parts of the system to the largest. When you look at a fossil in a museum, you're seeing one piece of that network, frozen in stone. But in life, it was all connected. The Earth 200 million years ago was not just the setting of the Jurassic. It was the force that shaped it. The drifting continents created new homes. The climate provided warmth and abundance. The plants built the green framework. The oceans nurtured marine reptiles and fish. The air carried sound and flight. Every detail tied together into a world that, if you could step into it, would surround you completely, pressing in with sights, sounds, smells, and textures that no movie or book can fully capture. And as the land kept moving, as seas kept widening, as volcanoes poured out their molten rock, life moved with it. Animals and plants never stopped adjusting. never stopped evolving. The Jurassic world was not frozen. It was always shifting, always alive. When you think about Earth during the Jurassic, one of the most important features to understand is the climate. The entire world was warmer than the one you know today, and it wasn't simply a matter of having hotter summers in certain regions. It was a planet operating under greenhouse conditions that meant higher average global temperatures, no permanent ice caps at the poles, and an atmosphere with more carbon dioxide than what you're breathing right now. It's a setting that shaped every forest, every shoreline, every creature that lived through that time. Without it, the dinosaurs you picture in your mind would never have been able to grow as large as they did, and the plants that filled the landscapes would never have reached the heights and spreads they achieved. What does it mean when scientists describe the Jurassic as a greenhouse world? To put it simply, the concentration of greenhouse gases such as carbon dioxide in the atmosphere was significantly higher than modern levels. Estimates vary, but some suggest it may have been 4 to 5 times higher than pre-industrial levels. That level of carbon dioxide trapped more heat in the atmosphere. The result was a global average temperature that stayed consistently warm. It wasn't just that summers were hot. Winters were milder. Even in places close to the poles, the planet had a smaller difference between its warmest and coldest regions, creating a kind of global warmth that made it possible for forests to reach far into higher latitudes, where today you'd expect tundra or ice. Because of this, the Earth during the Jurassic did not have permanent polar ice sheets. Imagine Antarctica, but instead of being covered in thick layers of ice, it hosted forests of conifers and ferns. Imagine the Arctic Circle without endless ice, but instead carrying vegetation that could support dinosaurs and other animals. That's not to say there were no cold periods or no variation. There were cooler seasons, there were dry spells, there were storms. But the overall picture was one of a much warmer and greener world, even at the edges of the globe. This greenhouse climate also meant sea levels were higher than they are now. With no vast ice caps locking water away, more of it was in liquid form, filling the oceans and causing them to spread farther inland. Shallow seas covered parts of the continents, creating coastlines where marine and terrestrial ecosystems overlapped. These shallow seas were full of nutrients, feeding coral reefs, shellfish, fish, and marine reptiles. They also provided hunting grounds for pterosaurs and other animals that lived near the edges of land and water. The rhythm of tides and waves was a central part of life for countless species. Rainfall patterns were different as well. With warmer oceans evaporating more water into the air, the atmosphere carried high amounts of moisture. That meant heavy rains in many regions, particularly near the coasts and along areas affected by monsoon-like systems. Some areas, especially inland parts of the continents, were drier, even arid, but overall the planet leaned toward being wetter. Lush forests grew in zones that had reliable rainfall, while deserts stretched across interior regions where moisture rarely reached. Together, these variations created diverse ecosystems, each with its own cast of plants and animals. Humidity was another defining characteristic of this greenhouse world. If you walk through a Jurassic forest, the air would feel heavy compared to what you're used to. The warmth combined with the moisture would press against your skin and fill your lungs with each breath. It would be the kind of climate where sweat clings, where shade under a conifer or cycad brings real relief, and where plants thrive in part because the conditions make photosynthesis efficient. This atmosphere created environments that could sustain enormous animals. When you look at a fossil of a sauropod stretching over 20 meters in length, part of the reason such a body was possible lies in the climate that supported endless supplies of plant matter. The higher oxygen levels also played a role. While carbon dioxide was elevated, oxygen levels were at times higher than modern concentrations as well. That made breathing efficient for large creatures and supported the growth of active animals that needed large amounts of energy. The air of the Jurassic wasn't exactly the same everywhere. Local conditions mattered, and oxygen concentrations may have fluctuated across millions of years. but overall it provided a breathable and supportive environment for both small and giant species. The skies themselves would have carried evidence of this climate. Clouds formed frequently, building into thick shapes that dropped heavy rains in bursts. Lightning storms swept across coasts and valleys. The sound of thunder would have been familiar to any creature living under those skies. Between storms, the sun poured heat onto the land. Days were long in the higher latitudes during summer, shorter during winter, just as they are now, but without the brutal freeze of icy winters, life could adapt to those shifts without facing extinction from cold. The greenhouse conditions of the Jurassic also helped stabilise ecosystems. With fewer sharp transitions between warm and cold seasons, plants could grow continuously in many areas. That stability meant herbivores had steady food supplies, and predators in turn had steady access to prey. It doesn't mean life was easy. Competition was fierce, and survival still required constant adaptation. But the climate provided a reliable framework, one where cycles of abundance could last long enough for evolution to experiment with size, shape, and behaviour. It's worth considering how this atmosphere influenced not just biology, but also geology. Warm, wet conditions accelerated weathering of rocks, feeding minerals into rivers and seas. That process helped support marine ecosystems by supplying nutrients. Volcanoes, frequent along the rift zones where continents were pulling apart, also released gases and ash into the air. Eruptions contributed carbon dioxide, feeding into the greenhouse system, but also temporarily shaded regions with ash clouds that could cool local climates for short periods. The interplay between constant warmth and occasional cooling pulses created variety in the environments animals experienced. The greenhouse atmosphere had direct effects on plants. Conifers, cycads, ferns and horsetails thrived in these conditions, spreading across continents. Some forests grew dense and towering, with canopies that blocked sunlight from reaching the forest floor. Others spread more openly, with space between trees where cycads clustered and ferns carpeted the gaps. In both cases, the constant warmth and moisture fueled growth. Photosynthesis was highly efficient with the elevated carbon dioxide levels, meaning plants could thrive even in conditions where modern species might struggle. That abundance translated into food for herbivores, which in turn supported predators, linking the atmosphere to the structure of entire ecosystems. Animals were directly influenced by the climate too. Sauropods needed huge amounts of vegetation to survive. The greenhouse world provided it. Stegosaurs and other plant-eaters browsed on ferns and cycads that grew in wide mats. Predators such as allosaurs and other theropods depended on the presence of those plant-eaters, and so the climate indirectly supported them as well. Insects flourished in humid environments, buzzing across forests and wetlands. Early birds and pterosaurs fed on them, linking the smallest parts of the ecosystem to the largest once again. This greenhouse world also meant migration patterns were different from what you might expect today. Animals could spread across wider ranges without being limited by cold zones. Forests reached into high latitudes, allowing herbivores to graze far north or south. The distribution of species was broader. Oceans too connected populations across large distances, with warm waters allowing marine reptiles and fish to occupy wide ranges. Life wasn't confined to narrow bands of habitability. It was spread broadly across a planet that, while always changing, offered warmth almost everywhere. Storms and rainfall had other effects. Rivers swelled during wet seasons, carrying nutrients and sediments across landscapes. Floodplains built up rich soils. Wetlands expanded and contracted with the seasons, creating habitats for amphibians, insects, and small reptiles. These seasonal rhythms gave structure to the year, even in a world without the sharp winters of today. Animals would have recognized wet and dry periods, abundant and lean times, and adjusted their behavior accordingly. The lack of permanent polar ice also meant ocean currents behaved differently. Today, part of the global circulation is driven by the sinking of cold, dense water near the poles. In the Jurassic, with warmer poles and no ice caps, circulation patterns were less extreme. Warm water could spread farther, helping maintain the even distribution of heat across the globe. That contributed to the overall mildness of the climate, keeping conditions stable for long stretches of time. When you imagine standing in that world, picture the heat pressing lightly on your skin, the air moist and rich, the forest around you alive with growth. Picture the sky building with clouds, releasing sudden rain that soaks the ground, feeding ferns and cycads, filling streams that run toward wide rivers. Picture nights that are cooler but not cold, stars overhead bright, the moon larger, tides stronger. That was the reality of the Jurassic atmosphere. It shaped every breath, every meal, every movement of the creatures that lived under it. The Earth today can shift toward greenhouse conditions too, though on smaller timescales, and we see hints of what such climates can do in tropical regions. But in the Jurassic, it wasn't just regional, it was global. That's why when you picture long-necked sauropods moving through conifer forests, or allosaurs stalking through humid valleys, you're seeing animals perfectly suited to the greenhouse Earth they inhabited. Their size, their abundance, their very existence was tied to that climate. The atmosphere itself was not static across the entire Jurassic. Conditions changed gradually over millions of years. There were pulses of volcanic activity that increased carbon dioxide further, followed by periods where levels declined slightly. Temperatures responded to those shifts, sometimes rising, sometimes falling, but always staying within a range much warmer than today. The Earth during this time operated under a balance that supported life at scales both massive and small. When you step back and think about it, the greenhouse climate of the Jurassic wasn't just background scenery. It was the engine that powered the age. It made it possible for plants to cover continents in green. It made it possible for herbivores to eat endlessly and grow to enormous sizes. It made it possible for predators to hunt across wide territories. It made it possible for oceans to fill with coral reefs, fish, and marine reptiles. It shaped migration, behaviour, and evolution itself. And as we continue to look deeper into the Jurassic, this atmosphere will always be there in the background, influencing every part of the story, When you picture Earth as it existed about 200 million years ago, one of the biggest differences from today was the way the continents were arranged. We often take the shapes of the continents for granted. Africa looks the way it does on a globe. South America has its familiar outline. North America sits like a great wedge above them. But in the Jurassic, those familiar pieces of land were still connected to each other as part of something much larger. That supercontinent was called Pangaea, and although it had already been around for millions of years, by the early Jurassic it was beginning to break apart. That process, slow as it seems to us, was one of the most important events in shaping the history of life on Earth. Pangaea stretched almost from pole to pole. Imagine a single landmass so vast that it combined nearly all of today's continents into one. On one side of it lay a single enormous ocean, Panthalassa. On the other, between northern and southern sections of the continent, lay the Tethys Ocean, narrower but vitally important as a cradle for marine life. When this continent began to fragment, it wasn't a matter of huge chunks suddenly drifting away like icebergs. Instead, deep within the Earth, heat from the mantle was driving convection currents. Those currents pushed against the plates above, and where stresses built up, cracks formed. Over time, those cracks widened into rifts, and those rifts filled with molten rock that cooled into new crust. That's how new oceans began. The Atlantic Ocean, which today separates Europe and Africa from the Americas, had its origins in this Jurassic rifting. At first, it wasn't an ocean at all, just a series of valleys opening slowly, sometimes flooded by seawater, sometimes filled with lava flows. With every passing million years, the separation grew. What you now recognize as the familiar coastlines of Brazil and West Africa once fit together like puzzle pieces, and in the Jurassic they were only beginning to drift apart. If you had been standing there, you wouldn't have seen continents racing across the globe. You would have seen long valleys with cliffs, volcanic activity along their edges, and shallow seas pooling into the gaps. The separation of land masses was something only visible when measured across immense spans of time. This movement had profound consequences for climate and ecosystems. While Pangaea had dominated the late Paleozoic and early Mesozoic, it created enormous continental interiors that were often dry and inhospitable. When land stretches too far from the moderating influence of oceans, rainfall has difficulty reaching the centre. That meant deserts were widespread in the heart of Pangaea. As the continent split, new coastlines formed, new seaways developed, and climates moderated in many places. Areas that had once been arid became wetter, supporting forests and more abundant vegetation. This change in turn provided food and habitats for animals, fueling evolutionary diversification. The separation also created barriers where none had existed before. When all the land was connected, animals and plants could in theory spread across vast ranges. But as seas formed between the pieces, populations were divided. Isolation is one of the drivers of evolution, because once groups are separated, they adapt to their own local environments. Over time, they become distinct species. The splitting of Pangaea set the stage for this process, ensuring that different regions of the world would develop their own unique ecosystems. Volcanic activity was closely tied to the rifting. As plates pulled apart, magma rose to fill the gaps. That produced lava flows that stretched for hundreds of kilometres, leaving behind layers of basalt that we can still see today in places such as eastern North America and northwest Africa. The eruptions released enormous amounts of gas into the atmosphere, including carbon dioxide, which fed into the greenhouse climate of the Jurassic. They also shaped the local landscapes, raising plateaus, building ridges, and altering drainage patterns. For the animals living nearby, eruptions were both destructive and transformative. Forests could be buried, rivers dammed, and coastlines reshaped. But in the long run, volcanic activity created new habitats and contributed nutrients to soils, supporting fresh growth once the eruption subsided. The formation of rift valleys left behind geological records that we can study today. Many of those rifts later filled with lakes, and the sediments deposited in those lakes preserved fossils. That's why paleontologists can find early Jurassic animals in formations such as the Newark supergroup in eastern North America. These rocks tell the story not just of the animals that lived there, but of the environment that formed as Pangaea broke apart. Fossilized fish, amphibians, reptiles, and plants all give evidence of the habitats that developed along those rift lakes. As the supercontinent separated further, two main land masses emerged. To the north was Laurasia, which included North America, Europe, and Asia. To the south was Gondwana, which held South America, Africa, India, Antarctica, and Australia. Between them stretched the Tethys Ocean. This division was not clean or sudden. Land bridges remained in some places, and animals could still move between certain regions, but the outlines of the world we know were beginning to take shape. The Tethys Ocean deserves special attention. It was warm, shallow, and biologically rich. Coral reefs flourished along its coasts, providing homes for countless marine species. Marine reptiles hunted in its waters, from ichthyosaurs shaped like dolphins to plesiosaurs with long necks and flippers. Fish filled the middle of the food chain, feeding on invertebrates and being eaten in turn. Ammonites, with their spiral shells, drifted through the seas, marking the Jurassic in the fossil record with their abundance and diversity. Without the Tethys, the marine life of the Jurassic would have looked very different. The movement of continents also influenced ocean currents. As seaways opened, they changed the flow of water around the globe. Warm currents carried heat into new regions, helping sustain the even climate of the greenhouse world. Nutrient cycles shifted, affecting where plankton and other microscopic life could thrive. Because these tiny organisms form the base of the marine food chain, Their distribution influenced everything above them, from small fish to massive predators. On land, the drifting continents influenced rainfall patterns. Mountains rose along rift margins, redirecting winds and creating rain shadows. Valleys collected moisture, turning into wetlands or lakes. The edges of continents received steady rainfall from oceanic winds. Inland areas that had once been deserts softened into savannas and forests. These changes in vegetation supported the spread of sauropods, stegosaurs and other herbivores, along with the predators that hunted them. It's worth pausing to imagine what this would have felt like if you lived in the middle of it. Standing in eastern North America, you might see a long valley stretching toward the horizon, filled with lakes and ringed by volcanoes. The air would smell faintly of sulphur after eruptions, and the ground would shake with tremors. Forests would regrow quickly in the fertile soils, and dinosaurs would move through them, browsing and hunting. Further south, along the margins of the Tethys, the scene would be very different. Warm, shallow seas lapped at sandy shores, coral reefs shimmered beneath the surface, and marine reptiles surfaced to breathe before diving back down. Inland, forests stretched across the landscape, their green canopy broken only by rivers winding toward the coast. These were not sudden transformations, but gradual ones. Generations of animals lived and died with no awareness of the slow drift, carrying their continents away from each other. Yet those movements were reshaping their futures. Populations that had once mingled freely became isolated. Over millions of years, that isolation produced new forms of life. This process explains why, later in the Mesozoic, the animals of South America looked different from those of Asia or North America. The breaking of Pangaea set in motion the regionalization of ecosystems that still defines our planet today. The evidence of this event is visible not only in rocks and fossils, but also in the very outlines of the continents. When you look at a map and notice how the bulge of South America fits against the curve of Africa, you're seeing the legacy of Pangaea's breakup. Those shapes are not coincidences. They are scars of the great split that began in the Jurassic. And along those scars, the Earth left clues about the animals and plants that lived there. What's remarkable is that the breaking of Pangaea did not just affect geology or biology in isolation. It intertwined them. As continents moved, climates shifted. As climates shifted, ecosystems changed. As ecosystems changed, evolution responded. It was a chain reaction with consequences that rippled across millions of years. And in the Jurassic, that chain reaction was only just beginning. The continents would continue to move throughout the Cretaceous and beyond, eventually reaching the arrangement we see today. But the Jurassic was the starting point of that journey. It was the time when the first cracks widened into seas, when the first barriers to migration appeared, and when the global climate began to take on the features shaped by separated land masses rather than a single unified block. And all the while, life carried on. Dinosaurs grazed in forests, predators stalked their prey, insects buzzed in the humid air, marine reptiles hunted in the Tethys, and the earth turned under the warmth of the sun. The breakup of Pangaea was a geological drama playing out over the backdrop of everyday survival. It's only by looking back now, with the perspective of millions of years, that we can see how enormous its impact truly was. The Jurassic was not only a time of shifting continents, it was also the beginning of new oceans taking shape, changing the face of the planet in ways that would ripple forward through every age that followed. Water has always been one of Earth's most powerful forces. It carves valleys, shapes coastlines, regulates climate, and provides a home for countless forms of life. During the Jurassic, as the supercontinent of Pangaea broke apart, new pathways for water opened, and the oceans responded by creating new currents, new coastlines, and new opportunities for life to expand. For millions of years before this period, much of Earth's surface had been dominated by one massive ocean, Pangaea. It stretched almost unbroken around the globe surrounding Pangaea. Within Pangaea, there were currents and ecosystems, but its vastness meant the world's marine life was concentrated along the supercontinent's coastlines. The interior of Pangaea was dry, far from the moderating influence of the sea. But once the great landmass began to fragment, water rushed into the gaps, forming new seas and reshaping old ones. The Atlantic Ocean traces its birth to this time, though in the early Jurassic it was just a narrow seaway in the making. It would take millions of years to widen into the massive body of water we recognise today, but the beginnings were already there. The Tethys Ocean, wedged between the northern and southern parts of the breaking continent, was one of the most biologically important regions of the Jurassic world. Warm, shallow, and full of nutrients, it served as a nursery for countless species. Coral reefs spread across its margins, building complex structures that housed fish, mollusks, crustaceans, and invertebrates of every description. These reefs acted as hotspots of biodiversity, much like modern reefs do. Above them, marine reptiles swam, including ichthyosaurs shaped for speed and plesiosaurs with their long necks and flippers. Ammonites, with their coiled shells, floated through the water in huge numbers. They became so common and widespread that their fossils now serve as key markers for dating Jurassic rocks. The rise of new seaways also meant the circulation of water around the planet shifted. Ocean currents are driven by temperature differences, wind patterns, and the arrangement of continents. With the continents breaking apart, new circulation paths opened. Warm currents spread heat more evenly across the globe, helping sustain the greenhouse climate. Nutrients carried by those currents supported plankton growth, which in turn fed fish, which then fed larger predators. The oceans of the Jurassic were not static pools but dynamic systems, pulsing with energy and life. Coastlines transformed dramatically during this time. As rifts widened and seas entered them, long stretches of new shoreline appeared. These coastlines provided habitats that didn't exist when Pangaea was fully intact. Estuaries formed where rivers met the sea, creating brackish environments rich in nutrients. Mangrove-like vegetation, though not yet the true mangroves of today, grew in some regions, stabilising sediments and supporting small animals. Sandy beaches stretched along other coasts, while cliffs and rocky shores dominated where rifting had created steep edges. Every new type of coastline brought with it new niches for organisms to occupy. The shallow seas that formed along continental edges were particularly important. Sunlight could penetrate their waters, fueling photosynthesis in algae and other microorganisms. These organisms formed the base of food webs that supported everything from small invertebrates to massive marine reptiles. Fossils of fish and reptiles from shallow sea deposits show how abundant life was in these areas. In some places, fossils are so dense that they suggest large gatherings of marine animals, possibly following seasonal migrations or congregating in areas where food was especially plentiful. Oceans also served as barriers and pathways at the same time. For animals tied to land, the new seas created divisions. Populations that had once mingled freely found themselves separated by stretches of water. Over time, those separations led to divergence, with isolated groups evolving into distinct forms. For marine animals, the seas were highways. The Tethys in particular connected east to west, allowing marine life to spread across vast distances. Its warm waters stretched from what would one day become the Atlantic to regions that would eventually form parts of Asia. The creatures that thrived there left fossils from Europe to the Middle East to Asia, showing just how wide their ranges were. Storms were part of this oceanic world too. Warm water feeds powerful weather systems, and with the Jurassic's greenhouse climate, the oceans were primed to produce them. Hurricanes and cyclones likely swept across shallow seas and slammed into coastlines. These storms reshaped beaches, flooded valleys, and destroyed vegetation along shores. But they also redistributed nutrients, stirring up sediments and enriching waters for plankton blooms. Life adapted to the cycle of destruction and renewal, just as it does today in modern tropical regions. The chemistry of the oceans was different as well. Higher levels of carbon dioxide in the atmosphere affected seawater just as they do now. The balance of carbonate ions influenced the ability of organisms to build shells and skeletons. Corals, mollusks, and ammonites all depended on that chemistry. Despite fluctuations, reefs flourished, suggesting that conditions, while not identical to today's, were favourable for calcifying organisms. Those reefs created three-dimensional habitats where countless smaller creatures could live, hide, and hunt. The presence of ammonites and other marine invertebrates in such abundance is a reminder of how critical the oceans were during this time. Ammonites were more than background creatures. They played an essential role in food webs. They fed on plankton and small animals, and in turn they were prey for fish and marine reptiles. Their rapid evolution and widespread distribution make them invaluable for paleontologists today, but in their own time, they were simply one of the most important links in the chain of marine life. Oceans also provided opportunities for terrestrial animals. Many dinosaurs lived near coasts where resources were abundant. River deltas, lagoons, and tidal flats would have drawn herbivores seeking plants and predators following them. Some footprints preserved in fossilized sediments show dinosaurs walking along ancient shorelines. The interaction between land and sea was constant, with animals and plants on each side influencing the other. The growth of new seas and currents also set the stage for future geological events. As continents drifted farther apart, the narrow seaways of the Jurassic widened. What began as rifts filled with water became fully developed oceans. These oceans influenced not only climate and ecosystems, but also human history much later. The Atlantic, which traces its beginnings to the Jurassic, would eventually become the body of water that shaped exploration, trade, and cultural exchange in our own time. But in the Jurassic, it was still young, still shallow, still learning its shape. The movement of water against coasts eroded rocks, carried sediments, and built deltas. These processes created environments where fossils could later form. That's why so many important Jurassic fossils are found in marine deposits. Fish, reptiles, ammonites, and even plants carried into the water by rivers became buried in sediments, preserved for millions of years until discovered. The oceans not only sustained life but also recorded it. If you could stand on a Jurassic coast, the view would have been striking. The horizon stretched across a warm sea. Waves lapped against sandy or muddy shores. Marine reptiles surfaced for air, their bodies glistening as they dove again. Ammonites floated in the shallows, their shells catching the sunlight. Fish darted in schools, scattering when a predator approached. Above, pterosaurs circled, their wings catching sea breezes as they searched for food. The air smelled of salt and vegetation, and the sounds of waves mixed with the calls of animals both on land and in the water. The oceans of the Jurassic were never quiet. They were places of constant energy, driven by tides, currents, and storms. They connected ecosystems, divided populations, and shaped the course of evolution. They were as central to life then as they are now, though the creatures that filled them were very different. Every coastline, every current, every shallow reef played a part in building the world of that time, and as the continents kept moving, the oceans kept adjusting. New coastlines appeared, old ones disappeared, currents shifted again, and life followed each change. The story of the Jurassic cannot be told without these oceans, because they were not just backgrounds, they were active forces, shaping everything that lived on the planet. When you imagine walking across the land during the Jurassic, the very first thing surrounding you would not be the dinosaurs, but the plants. Before you ever spotted a giant sauropod or heard the call of a predator, you'd be standing in landscapes that were defined by towering trees, sprawling ferns, and dense thickets of cycads. These plants created the framework of the entire ecosystem. They shaped the climate locally, fed the herbivores, sheltered the smaller animals, and determined what kinds of habitats existed for millions of years. If you stripped them away, the Jurassic world would collapse into silence. Grasses didn't exist yet. The great open meadows and savannas that feel so natural to us today were not part of the scenery. Instead, the ground was covered with layers of ferns. They spread like living carpets, filling the understory with their wide fronds. Some of these ferns grew low, hugging the soil, while others reached several feet in height, forming waist-high or chest-high expanses of green. Moving through them would have been like pushing through fields of giant leaves, each frond unrolling in spirals during its early growth before flattening into the fan-like shape we still see in modern ferns. They thrived in the humid air, taking advantage of the moisture and warmth that the Jurassic atmosphere offered. Their spores spread easily, carried by wind and water, ensuring that wherever conditions were right, ferns established themselves in thick, almost endless numbers. Above them grew cycads. These plants were unlike anything most people are used to today, though a few species still survive in tropical and subtropical regions. Cycads look a little like palms, with stout trunks and a crown of stiff feather-like leaves radiating from the top. In the Jurassic, they came in many shapes and sizes. Some were only a few feet tall, creating clusters that dotted the landscape. Others were larger, their trunks thicker and their crowns reaching overhead. They reproduced using cones rather than flowers, because flowering plants hadn't yet evolved. Their seeds were protected by tough outer shells, which meant they could survive harsh conditions and spread to new areas. Dinosaurs fed on cycads, tearing at their leaves and occasionally chewing through their cones. These plants were resilient, able to recover after being grazed, which allowed them to persist even in environments full of massive herbivores. Then there were the conifers, the true giants of the forests. These were not exactly the same species you might know from pine or spruce forests today, but they belonged to the same broader family. Some of them were immense, reaching heights of more than 100 feet, their trunks straight and tall, their branches covered in needles. They dominated large areas of the Jurassic landscape, especially in regions with consistent rainfall. Their wood was tough, their bark thick, and they could stand for centuries, forming forests that stretched for miles. These conifers provided the backbone of the Jurassic plant world. Their needles fell to the ground and accumulated, breaking down slowly and enriching the soil. Their cones dropped seeds that scattered in the wind, creating new trees. Their branches shaded the forest floor, shaping what could and couldn't grow beneath them. Walking into one of these forests would have been an overwhelming experience. The scale alone would make you feel small, trunks wider than a person's arms could reach, stretching upward into canopies that blocked much of the sky. The air under those trees would be cooler and damper, filled with the smell of resin. Ferns grew thick in the shadows, cycads clustered in the lighter spots, and horsetails sprouted in wet soils near streams. The sounds of animals echoed between the trees, but the plants themselves formed the structure that everything else depended on. Horsetails deserve their own mention. Today, the few species that survive are small plants you might see along riverbanks, their hollow stems no more than knee-high. But in the Jurassic, horsetails could grow much taller, sometimes up to 30 feet. They formed dense stands in swampy areas, their segmented stalks rising in straight lines, topped with brush-like clusters of spore-bearing cones. These plants thrived in wet conditions, anchoring the edges of lakes and rivers, providing cover for small animals, and stabilizing soils against erosion. Their presence gave the Jurassic wetlands a very different look than anything you'd see today. What's important to realize is that all these plants existed long before flowering plants came onto the scene. There were no colourful blossoms attracting pollinators, no meadows filled with petals, no fruit hanging from branches. Pollination in the Jurassic was simpler. Wind carried spores from ferns and horsetails. Conifers and cycads relied on cones, some of which used wind and others that involved insects, though not in the complex ways modern flowers do. This meant the landscapes were overwhelmingly green. Shades of green dominated every horizon, from the deep dark greens of conifer needles to the lighter greens of ferns. Seasonal changes were subtle compared to today's temperate forests. Leaves didn't blaze into reds and yellows in autumn. Instead, most of the plants were evergreen. keeping their foliage year-round, with only gradual cycles of growth and decay. These forests were more than just backdrops. They drove the energy of the ecosystem. Herbivores fed directly on them, stripping leaves, chewing needles, gnawing on branches. Insects burrowed into their stems and trunks. Fungi broke down fallen material, recycling nutrients back into the soil. The abundance of plant life made it possible for massive animals like sauropods to exist. Without endless supplies of foliage, there could never have been creatures stretching 80 feet long, needing hundreds of pounds of food every day. The plants carried the weight of those giants, and in return the giants shaped the forests. When a sauropod moved through a stand of trees, it pulled down branches, opened gaps in the canopy, and allowed light to reach the understory. Smaller plants took advantage of those openings, creating cycles of disturbance and regrowth. Fossil evidence tells us that many of these plants left behind thick accumulations of debris. In some regions, those deposits turned into coal over millions of years. Coal seams from the Jurassic show us just how extensive and productive these forests were. Layer upon layer of compressed plant material speaks of ecosystems that grew, died, and renewed themselves on vast scales. These deposits remind us that plants were the real foundation of the Jurassic, just as they are today. Imagine walking across different regions. In lowlands near rivers, you'd find wetlands dominated by horsetails and ferns, buzzing with insects and croaking with amphibians. A little higher up, cycads would cluster, their stiff leaves forming dense patches where small reptiles and early mammals could hide. In drier uplands, conifer forests would dominate, their tall trunks creating shaded paths beneath them. Each environment had its own feel, its own smells, its own sounds, yet all of them were tied together by the same greenhouse climate that allowed so much green life to thrive. It's also worth considering how fire interacted with these forests. Warmer, wetter conditions meant frequent storms, and lightning strikes could ignite vegetation. Some of the plants, like certain conifers, were adapted to survive fire. Their thick bark protected their trunks, and their cones could open after heat, releasing seeds into freshly cleared ground. Fires would have burned patches of forest, creating mosaics of regrowth across the landscape. Dinosaurs and other animals would have moved in response, fleeing the flames, then returning to graze on the tender shoots that sprang up afterward. Fire was part of the natural cycle even in the Jurassic. The presence of these forests also influenced the atmosphere itself. Plants constantly exchange gases with the air, taking in carbon dioxide and releasing oxygen. With so much vegetation covering the planet, oxygen levels rose. This helped support not only the massive herbivores and predators, but also smaller, more active animals that required efficient breathing. The forest literally made it possible for life to reach the scales and levels of activity we associate with the Jurassic. Even the smallest details of these plants mattered. Fern spores, scattered on the wind, carried genetic diversity far and wide. Conifer cones, sometimes the size of a person's head, dropped seeds that could survive long journeys before sprouting. Cycad seeds were often encased in tough shells, protecting them from predators until they could find a safe place to grow. Horsetails spread by underground rhizomes as well as spores, ensuring they could reclaim ground quickly after disturbances. These strategies allowed the plants to persist despite the constant pressure of being eaten, trampled, or burned. For animals, the forests were not just food sources, they were homes. Small mammals built burrows under fern mats. Insects laid eggs inside cycad leaves. Pterosaurs perched on conifer branches. Dinosaurs nested in clearings created by fallen trees or along the edges of wetlands where vegetation provided cover. The plants structured every level of life, from the tiniest burrows to the tallest nests. When you think of the Jurassic, it's tempting to let your imagination focus on teeth and claws. But without the forests of conifers, cycads, ferns, and horsetails, those teeth and claws would have had nothing to bite into. The plants were the stage, the script, and the supporting cast. Everything else, no matter how impressive, was dependent on them. If you lowered your gaze from the towering conifers and cycads of the Jurassic, what would have stretched out at your feet was something just as vital, even if it was easier to overlook. Ferns dominated the ground in ways we can hardly imagine today. Instead of vast fields of grass waving in the wind, you would have found expanses of fern prairies. These were green carpets rolling across lowlands, floodplains, and the open patches between forests. They weren't uniform either. Some prairies were made up of small, low ferns hugging the ground, their fronds spreading wide in circles that overlapped until there was hardly any bare soil left. Others were filled with taller ferns, waist-high or higher, forming thick stands that an animal would need to push through to cross. These fern prairies were essential to the balance of the ecosystem. They took advantage of the greenhouse conditions of the Jurassic, soaking in moisture, thriving in warmth, and reproducing through spores carried easily by the wind. Unlike seeds, spores didn't need pollinators or specific conditions to spread. A single breeze could scatter millions of them across the landscape. That meant ferns could colonize open ground quickly, especially after disturbances like fire or floods. When a patch of forest fell to storm damage or a volcanic eruption cleared part of a valley, ferns were often the first plants to return, covering the bare soil in green within a short time. The animals of the Jurassic depended on these prairies more than you might expect. Large herbivores grazed on them, stripping fronds with their beaked mouths or broad teeth. Smaller dinosaurs darted into them for food and cover. Early mammals scurried along their edges, using the low foliage for shelter. Insects thrived in these environments as well, feeding on the soft plant tissue or laying eggs on the undersides of fronds. Fern prairies were like living dining halls and protective shelters all at once. They provided food at the bottom of the food chain, which supported everything higher up. But the ferns didn't just cover the open landscapes, they also dominated the understory of the great forests. Walk beneath the conifers, where the canopy blocked much of the sunlight and the ground wouldn't be bare. It would be filled with ferns growing wherever enough light filtered through. They formed a continuous layer of greenery beneath the towering trees, a second forest beneath the first. This understory created a unique world of its own. The air was cooler there, damper, with a constant smell of soil and vegetation. Smaller animals moved through it, largely hidden from view. Predators hunting in the forest had to listen for rustling in the ferns to find their prey. The understory was a living maze, shaping how animals moved and how they survived. Different types of ferns filled different niches. Some species preferred the shade and thrived under the canopy. Others needed more sunlight and spread across open prairies and floodplains. Some grew in swampy soils, their roots adapted to waterlogged conditions. Others clung to rocky outcrops, spreading their fronds into the light. This diversity ensured that ferns were present almost everywhere. In many ways, they were the defining plants of the Jurassic landscape, more common than cycads, and even more widespread than conifers in certain areas. The resilience of ferns came from their simple but effective reproductive strategy. By producing vast numbers of spores, they could overwhelm the odds. Even if most spores didn't take hold, enough did to ensure the spread of new plants. Their ability to grow quickly allowed them to outcompete slower plants in disturbed areas. This resilience is one reason ferns have survived for hundreds of millions of years, long past the Jurassic, and still exist today. They were survivors in a world full of giants. For the animals that relied on them, ferns were both food and cover. Imagine a herd of stegosaurs moving across a fern prairie. Their beaked mouths cropped the fronds methodically, clearing patches as they went. Behind them, smaller dinosaurs followed, taking advantage of the gaps to find insects or new shoots. Predators like allosaurs might have stalked along the edges, waiting for a moment when an individual strayed too far from the group. In that way, the fern prairie wasn't just a patch of plants. It was a stage where life and death played out daily. The understories beneath conifer forests played an equally important role. In those dim green spaces, smaller herbivores could move without being seen. Early mammals, no larger than a mouse or rat, tunneled through the soil and darted between fern stems. Insects hummed softly, feeding on decaying plant matter as much as on living fronds. Amphibians croaked in damp hollows. The whole layer buzzed with life, even though the towering trees above captured most of the attention. To the smaller creatures, the understory was the world. Fossil evidence confirms the abundance of these plants. Many Jurassic rock formations preserve impressions of fern fronds, their shapes pressed into mud that later hardened into stone. These fossils are often so detailed that you can see the veins running through the leaves. They tell us that ferns weren't just scattered here and there, they were everywhere, covering entire landscapes. Some deposits are almost pure beds of plant material, showing how thick and dense the growth was. The contribution of these plants went beyond food and cover. They shaped soils by trapping moisture and preventing erosion. Their fallen fronds decomposed into layers of organic material, enriching the ground. This created fertile conditions for other plants to grow, supporting cycads and even young conifers. They played the same role grasses play in many modern ecosystems, binding soils and recycling nutrients. Without them, Jurassic landscapes would have been far more unstable. It's also important to think about the role of ferns in fire recovery. Lightning strikes set forests ablaze, and volcanic eruptions scorched wide areas. After such events, ferns were almost always the first to return. Their spores spread into the ashen soil, germinating quickly. Within a short time, blackened ground would be covered in green once more. These early waves of ferns created conditions for cycads and conifers to return, rebuilding forests step by step. In this way, ferns acted as pioneers, always ready to reclaim disturbed land and restart the cycle of growth. The fern prairies also created unique challenges for the animals that lived within them. Moving through thick stands of waist-high fronds wasn't easy. Small animals could vanish into them, but larger animals had to push their way through, leaving trails behind. Predators learned to follow those trails, waiting for moments when prey exposed themselves. The prairie wasn't just food, it was also a battleground where cover and visibility decided survival. Under the conifer canopies, the understory ferns shaped the way animals interacted too. The dim light meant vision wasn't always reliable. Animals had to rely on sound and smell to navigate. The rustle of a frond could mean a predator, or it could mean nothing more than a small lizard. To an early mammal hiding under a fern, every sound carried potential danger. The forest floor was a constant game of risk and chance, played out among leaves that towered above creatures too small to see the world beyond them. These plants also influenced the appearance of the world in ways that would feel very different from what we know today. Imagine walking into a modern forest, and then imagine replacing the grasses and flowers with endless ferns. Instead of bright colours breaking up the green, you'd see subtle variations of green everywhere. Instead of wide-open meadows, you'd walk through fern fields that reached your waist. Instead of flower scents drifting on the air, you'd smell resin from conifers, damp soil, and the faint must of fern spores. The Jurassic had its own atmosphere, one created by plants that had not yet given way to the diversity of flowering species that dominate today. Everywhere you looked, the plants created structure for animals to live within. A herd of sauropods crossing a floodplain would have left behind trampled patches of ferns that regrew within weeks. Smaller herbivores grazing in clearings maintained open spaces where predators could spot them. Early birds flapped between cycads that rose from fern carpets. Insects moved from frond to frond, carrying spores on their bodies by accident. All of it worked together as one system. The persistence of ferns into the present day is a reminder of how successful they were. They may not dominate landscapes now the way they did in the Jurassic, but their survival proves the effectiveness of their strategy. They didn't need flowers or fruit. Their spores and fronds carried them across millions of years. And in the Jurassic, when conditions favoured their growth, they spread with astonishing success, filling every available niche from open plains to shaded understories. The The fern, prairies and understories of the Jurassic were not just background details. They were the canvas on which the entire ecosystem was painted. They provided the base layer of food and shelter, influenced the soil and atmosphere, and gave smaller creatures the ability to survive in a world ruled by giants. To understand the Jurassic fully, you can't just look up at the towering dinosaurs. You also have to look down at the fronds brushing against your legs, the green mats under your feet, and the understory stretching into the shadows. When you turn your focus from the land of forests and ferns to the waters of the Jurassic, the picture shifts dramatically. The seas of that time were just as full of life as the landscapes, but the creatures that filled them looked very different from what you'd expect if you dipped beneath the waves today. They were alive with reptiles that had adapted to the marine world, fish that were ancestors of modern groups, and invertebrates like ammonites that floated in the currents by the millions. These oceans were not quiet or empty. They were busy, competitive, and shaped by predators and prey locked in constant cycles of survival. The most iconic marine reptiles of the Jurassic were the ichthyosaurs. They had first appeared earlier in the Triassic, but by the Jurassic they had reached their peak diversity. Their bodies looked remarkably like dolphins, though they were reptiles and not mammals. Streamlined and built for speed, they had long, pointed snouts filled with teeth, large eyes that gave them excellent vision in dim light, and tails shaped with downward-turning flukes that powered them through the water. Fossils show that some species reached lengths of more than 15 meters. Imagine a reptile the size of a bus darting through the ocean, hunting fish, squid, and smaller reptiles with precision. Ichthyosaurs were among the fastest swimmers of their age, their entire bodies adapted for life in the open sea. One of the most fascinating things about ichthyosaurs is how closely their bodies resembled dolphins and tuna, animals that would not evolve until much later. This is an example of convergent evolution, where unrelated species develop similar shapes because they face similar challenges. To move quickly and efficiently through water, there are only so many solutions nature can arrive at, and ichthyosaurs found one that worked perfectly. Fossilized stomach contents even reveal their diets. Some contain fish bones, others contain remains of squid-like creatures, and some even show that ichthyosaurs fed on smaller ichthyosaurs. They were versatile hunters in a world where speed often meant survival. Then there were the plesiosaurs. Unlike ichthyosaurs, their bodies did not resemble modern ocean predators as closely. They had broad, flat bodies powered by 4 strong flippers, which they used in a motion that resembled flying underwater. Some species had extremely long necks, with small heads at the end, while others had shorter necks and larger heads built for crushing prey. The long-necked forms are often the ones most people imagine, sometimes even inspiring myths of sea serpents in later times. They could stretch their necks out into schools of fish, snapping up prey with quick bites, or dart into shoals of smaller animals without needing to move their entire bodies. Fossils suggest some plesiosaurs exceeded 12 meters in length, their necks alone stretching several meters. These animals were not fast in the same way ichthyosaurs were, but their 4-flippered swimming gave them agility and control. They could maneuver in ways that made them efficient hunters even without top speed. Plesiosaurs occupied a wide range of ecological roles. Some were specialists focusing on fish and squid. Others may have gone after tougher prey, using stronger jaws to break shells or tackle larger animals. Their presence in the oceans shows just how diverse the marine reptiles of the Jurassic were. Different body plans solved the same problem in different ways, filling the seas with predators that rarely looked alike but often overlapped in what they hunted. Among the most powerful marine reptiles of the Jurassic were the pliosaurs, a group closely related to plesiosaurs but with much shorter necks and massive heads. They were apex predators, some growing up to 15 meters long. Their jaws were filled with teeth as long as bananas, capable of crushing bone. Pliosaurs hunted anything they could catch, including fish, squid, and even other marine reptiles. Fossil evidence suggests they were the terror of the seas, as dominant in their environment as tyrannosaurs would later be on land. Imagine swimming in a Jurassic Sea and seeing a massive head rise from the depths, jaws opening wide enough to engulf you whole. That was the reality for smaller creatures unlucky enough to cross paths with a pliosaur. The fish of the Jurassic were just as important as the reptiles. They filled the oceans in staggering numbers, providing the base of the food web for predators like ichthyosaurs and plesiosaurs. Many were early relatives of modern groups such as teleosts, which today make up the majority of fish species. Jurassic fish included both small schooling species that darted in huge numbers and larger, solitary hunters that prowled reefs and open waters. Their scales and bones are found in abundance in fossil deposits, often alongside ammonites and marine reptiles, showing how interconnected these ecosystems were. Sharks were present as well. They had already been around for hundreds of millions of years, and in the Jurassic, they continued to thrive. Some were small, feeding on fish and invertebrates. Others were larger, capable of challenging reptiles for dominance in certain niches. Sharks never reached the size of pliosaurs during this time, but their adaptability ensured they survived alongside these giants. Fossils of Jurassic sharks include teeth that show a wide variety of shapes, from slender needles for grasping slippery prey to broad serrated forms for slicing flesh. This diversity made them resilient, able to exploit whatever opportunities the oceans provided. Ammonites are worth returning to, because their presence defines the Jurassic seas more than almost any other creature. These mollusks, relatives of squid and octopuses, lived inside coiled shells. They floated through the water using jet propulsion to move, and their tentacles extended from the opening of their shells to catch prey. Ammonites came in countless shapes and sizes. Some were only a few centimeters across, while others reached more than a meter in diameter. Their shells were beautifully patterned and divided internally into chambers, which they filled with gas or fluid to control buoyancy. They were so widespread and evolved so rapidly that paleontologists used them to identify the age of rock layers. In their own time, they were central prey items supporting fish, reptiles, and even seabirds that were beginning to appear. Coral reefs provided another key feature of Jurassic oceans. Built by coral polyps secreting calcium carbonate, these reefs stretched across warm, shallow seas, especially in the Tethys Ocean. They provided structure where countless species could live. Small fish darted between the branches of corals, hiding from predators. Crustaceans scuttled across the reef floor. Sponges and mollusks attached themselves to the surfaces. The reefs themselves were ecosystems, buzzing with life in every niche. Above them, reptiles hunted the fish that gathered there, making the reefs hotspots of both diversity and danger. The interaction between land and sea was constant. Rivers carried nutrients from forests and prairies into the oceans, feeding plankton blooms near coastlines. These nutrients supported food chains that extended from microscopic algae all the way up to marine reptiles. Dinosaurs occasionally left footprints on tidal flats, some of which are preserved in fossils showing where they interacted with the sea. Pterosaurs, the flying reptiles of the time, soared above the waters, diving to catch fish or scavenging along coasts. The line between terrestrial and marine ecosystems was blurry, with energy flowing back and forth across it every day. The Jurassic oceans were not without hazards. Storms swept across them, driven by the greenhouse climate's warm waters. Hurricanes and cyclones battered coastlines, smashing reefs and reshaping beaches. Eruptions near rift valleys sometimes poured lava into shallow seas, killing local life but creating new habitats once the rock cooled. Predators prowled constantly, making every swim a matter of risk. Yet the abundance of life meant that for every loss, new growth quickly followed. Populations rebounded, species adapted, and ecosystems continued to flourish. If you could dive into a Jurassic Sea, the experience would overwhelm the senses. Light would filter down through clear, warm water, glinting off the shells of ammonites and the scales of fish. Schools of fish would swirl around you, parting as an ichthyosaur shot past in pursuit. In the distance, a plesiosaur would glide, its neck weaving through the water as it snatched prey. Beneath you, a coral reef would stretch in intricate patterns, buzzing with small movements. Then, suddenly the shadow of a pliosaur might loom, massive jaws opening, reminding you that this was a world where survival was never guaranteed. The oceans of the Jurassic were every bit as important as the forests and prairies of the land. They were engines of evolution, arenas of competition, and sources of abundance. They supported life on scales both small and massive, connecting everything from plankton to apex predators. They were restless, shaped by currents and storms, yet stable enough to sustain ecosystems for millions of years. Without them, the Jurassic would not be remembered as one of the most vibrant periods in Earth's history. When you picture the oceans of the Jurassic, one of the most important features to keep in mind is the coral reef. These underwater structures were not just clusters of colourful growth. They were entire ecosystems, built slowly over time by tiny organisms that left behind limestone skeletons. Those skeletons accumulated, forming massive reefs that stretched for miles and rose into intricate shapes. In the Jurassic, reefs spread widely across warm, shallow seas, especially in the Tethys Ocean, which ran between the northern and southern land masses of the time. These reefs were cradles of life, supporting an extraordinary range of species and influencing the survival of creatures in the seas around them. The corals of the Jurassic were different in some ways from those that dominate reefs today. Modern reefs are mostly made by scleractinian corals, which also existed in the Jurassic, but they shared space with other reef builders, such as sponges and algae. These groups combined their efforts over thousands and millions of years, each generation adding new layers of calcium carbonate to the structures beneath them. The result was an environment that provided shelter, food, and protection for countless animals. The reef was never quiet or still. At any given moment, small fish darted in and out of coral branches, using them as hiding places when predators swam past. Crustaceans scuttled along the reef floor, scavenging bits of food from crevices. Mollusks attached themselves to the hard surfaces, filtering water for nutrients. Sponges anchored themselves firmly, pumping water through their pores to extract food. The reef was alive with constant motion, even though its foundation looked solid and permanent. Every part of it was buzzing with activity, from the tiniest polyps building the reef upward to the largest predators circling overhead. One of the most striking aspects of these reefs was the density of life they supported. In open water, creatures had to swim constantly, competing for food in a three-dimensional environment with few places to hide. On the reef, life packed itself into a maze of structures. This density created opportunities for specialization. Some fish evolved body shapes that allowed them to slip between narrow coral branches. Others developed strong jaws for crushing shells. Crustaceans adapted claws for breaking open mollusks or scraping algae from hard surfaces. The reef was like a city, filled with niches for every kind of life. The reefs also provided nurseries for young animals. Many species used them as safe places for early growth, before moving into open waters as adults. Juvenile fish hid in the coral to avoid predators. Ammonites may have hovered near reefs during vulnerable stages of their lives, using the structures as protection against larger hunters. Even some marine reptiles may have come close to reefs at certain times, drawn by the abundance of smaller prey clustered there. These nurseries ensured that the reef wasn't just a shelter for current populations, but also a breeding ground for the future. Predators were never far away. Ichthyosaurs patrolled the waters around reefs, darting in to grab fish that strayed too far from cover. Plesiosaurs glided through, using their long necks to probe into shoals of fish that swarmed near the structures. Sharks circled, waiting for opportunities to strike at weak or distracted prey. The density of life on the reef attracted predators just as surely as it attracted smaller creatures, turning the area into a place of constant vigilance. For every fish that found food among the corals, Another risked becoming food itself. The reef also shaped the chemistry of the water around it. By building layers of calcium carbonate, corals and other reef organisms influenced how carbon moved through the environment. Their structures helped buffer local conditions, creating stable microhabitats even when currents shifted. Algae living in symbiosis with corals contributed oxygen and sugars, feeding the polyps that built the skeletons. This relationship, ancient and delicate, was part of what made reefs so successful. Even in the Jurassic, with its higher carbon dioxide levels, reefs found ways to thrive, expanding across warm, shallow seas in long bands that paralleled coastlines. For paleontologists, reefs are goldmines of information. Fossil reefs preserve not only the skeletons of corals themselves, but also the creatures that lived among them. Fish bones, mollusk shells, ammonite fragments, crustacean claws, even the occasional marine reptile remains have all been found in reef deposits. These fossils provide snapshots of entire ecosystems, not just single species. They reveal how many different forms of life crowded into the same environment, interacting in ways that shape their evolution. The presence of reefs also affected the larger geography of the seas. They acted as barriers, breaking waves before they reached shorelines, creating lagoons behind them and influencing sediment patterns. Those lagoons often became rich habitats of their own, filled with calmer waters where delicate species could thrive. Reefs changed water flow, shaped currents locally, and provided resting points for creatures that needed to pause in their journeys. They were engineers of the ocean as much as they were homes for animals. Imagine swimming through one of these Jurassic reefs. The water would be warm and clear, sunlight cutting down in shifting beams. Every surface would be alive with shapes and colours, not the same colours you'd see in a modern reef perhaps, but still a riot of movement and form. Fish dart in schools, scales flashing. Ammonites drift, their tentacles reaching out. Crabs crawl sideways across sandy bottoms, disappearing into crevices at the first sign of danger. An ichthyosaur passes overhead, its sleek body a shadow that briefly darkens the reef before it disappears into the blue. Life is everywhere, layered upon itself, each creature finding a place in the maze of coral. The reefs of the Jurassic were also resilient. Storms battered them. Volcanic activity dumped ash into the seas. Currents shifted. Yet the corals and their allies rebuilt, generation after generation, adding new skeletons on top of old, turning damage into opportunity. Over millions of years, these reefs grew into massive structures, some of which still survive in fossil form today. Those fossils tell us that reefs weren't just temporary habitats. They were permanent fixtures of the ocean, as reliable in their presence as forests were on land. Their importance cannot be overstated. Without reefs, the biodiversity of the Jurassic seas would have been far lower. The open ocean could never have supported such dense populations of fish, mollusks and crustaceans on its own. The reefs concentrated life, making it possible for predators to flourish and ecosystems to stabilize. They were cradles of life, shaping everything around them, just as they do today. And beyond the reefs, the ocean stretched outward, carrying currents that spread life to distant shores. The reefs were not isolated. They connected to the larger world, feeding and being fed by it, part of the constant exchange that kept the Jurassic seas alive. When you think of the Jurassic on land, there is one image that rises above all the rest, and that is the Sauropod. These enormous dinosaurs were unlike anything alive today, and even though we can compare them loosely to elephants or giraffes in terms of size or feeding habits, the truth is that they were something altogether unique. They were the largest animals ever to walk on Earth, and their presence defined the landscapes they inhabited. Entire ecosystems bent around their needs, because when an animal stretches more than 20 meters in length, with a neck longer than a bus and a body weighing dozens of tons, it doesn't simply live in an environment, it transforms it. The most familiar sauropods include Brachiosaurus, Diplodocus, Apatosaurus, and their relatives. Each had its own shape, but they all shared certain defining features. Their necks were extraordinarily long, made up of a series of elongated vertebrae that allowed them to reach vegetation far above the ground. Their bodies were massive, supported by 4 thick legs that acted like pillars. Their tails were often just as long as their necks, used for balance, defense, or even communication. Their heads were small compared to their bodies, but their teeth were adapted for stripping leaves efficiently. Everything about them pointed toward one purpose: consuming vast amounts of plant matter to fuel their enormous bodies. Fossils show us that these giants travelled in groups, and that behaviour makes sense when you think about survival. A single sauropod, no matter how large, was still vulnerable to predators, especially when young. But in herds, they had protection. Adults could circle around the young, presenting walls of massive bodies and swinging tails to ward off attackers. Moving in groups also helped them manage their constant need for food, since travelling together meant they could cover large areas systematically, stripping one region of vegetation before moving on to another. Their footprints, preserved in trackways across ancient floodplains, reveal parallel lines that suggest coordinated movement. These tracks are some of the most direct evidence we have of their social behaviour. Feeding was at the centre of everything they did. A sauropod needed to eat hundreds of pounds of vegetation each day just to survive. Their long necks gave them access to food other animals couldn't reach, from the tops of conifer trees to mid-level cycads and ferns. Some, like Brachiosaurus, carried their necks high, browsing at levels that few others could touch. Others, like Diplodocus, had necks that extended horizontally, sweeping through ferns and low vegetation in wide arcs. By dividing the available food sources this way, sauropods could share the same landscapes without directly competing for the exact same plants. This partitioning helped sustain multiple species side by side, each taking a different slice of the environment. The digestive systems of sauropods were just as important as their feeding strategies. They didn't chew their food the way mammals do. Their teeth were suited for stripping and grabbing, not grinding. That meant most of the actual breakdown of plant matter happened inside their massive guts. Many paleontologists believe sauropods swallowed stones, called gastroliths, which helped grind tough plant material in their stomachs. Combined with long, digestive tracts and microbial fermentation, this system allowed them to extract energy from plants that would be difficult for smaller animals to digest. Their enormous size was both a cause and a result of this digestive efficiency. Larger bodies could house larger digestive systems, which in turn made it possible to process more food and grow even larger. Their size brought other advantages too. Being massive made them harder targets for predators. A full-grown sauropod would have been nearly impossible for even the largest Jurassic carnivores to bring down. Predators likely targeted the young, the sick, or the isolated because adults in their prime were simply too big. Size also helped sauropods regulate their body temperature. Large animals lose heat more slowly, which meant sauropods could maintain stable internal temperatures despite fluctuations in their environment. In a greenhouse world, this stability was an advantage, keeping them active across a range of conditions, but size came with challenges. Moving such enormous bodies required powerful muscles and efficient skeletons. Sauropods developed unique bone structures that made their bodies both strong and light. Their vertebrae were filled with air sacs connected to their respiratory systems, reducing weight while still maintaining strength. These air sacs also helped them breathe more efficiently, pulling oxygen deep into their bodies. This system is similar to what we see in modern birds, which are descendants of smaller theropod dinosaurs. In sauropods, it allowed them to sustain activity and growth that would otherwise have been impossible. The growth of these animals was astonishing. Fossil evidence shows that sauropods hatched from eggs no larger than a football. To reach lengths of 20 meters or more, they had to grow rapidly, putting on tons of weight in just a few decades. This growth required immense amounts of food and efficient metabolisms. Their life histories were shaped by this pressure to grow quickly enough to escape predation and reach sizes where they were safe. It's likely that many young sauropods didn't survive those early years, but the ones that did became nearly untouchable giants. The impact of sauropods on their environment was profound. Moving through forests, they knocked down trees, opened gaps in the canopy, and reshaped the vegetation. Their feeding created pathways and clearings. Their dung fertilized the soil, spreading nutrients and seeds. Their migrations ensured that plant life was constantly disturbed and renewed. In this sense, sauropods were ecosystem engineers, influencing the landscapes as much as they were shaped by them. The structure of Jurassic forests and prairies cannot be separated from the presence of these animals. Even their tails added to their role. Some species had tails that may have acted like whips, capable of creating cracks loud enough to startle predators or communicate across distances. Others used their tails simply for balance, countering the weight of their long necks. The sheer variety of sauropod form shows how evolution experimented with different solutions, all within the framework of enormous plant-eating bodies. Diplodocus had extremely long, slender tails. Brachiosaurus had a body plan with longer front legs, raising its shoulders high and giving it a giraffe-like stance. Apatosaurus carried a more horizontal profile, sweeping through low vegetation. Each adaptation reflected a different way to survive in the same world. Fossil sites from the Jurassic often contain the remains of multiple sauropods together. These assemblages suggest that they lived and died in groups. Sometimes entire herds may have perished in floods or droughts, leaving behind bone beds that paleontologists uncover millions of years later. These sites give us windows into their social lives, their sizes, and their behaviours. Trackways show adults walking alongside juveniles, reinforcing the idea that herding and protection of young were part of their strategy. The sheer presence of sauropods must have been awe-inspiring to any creature that shared their world. Imagine standing on a Jurassic floodplain and seeing a herd of Brachiosaurus in the distance, their necks swaying above the treetops, their bodies moving slowly but steadily across the landscape. The ground might shake faintly beneath their weight. Their calls, deep and resonant, could carry across long distances, communicating with others in the group. To smaller animals, they would have seemed like moving hills, massive and unbothered by most threats. But they weren't invincible. Disease, drought, volcanic eruptions, and predation on the young all took their toll. Their survival depended on constant adaptation to the challenges of their environment. Yet for millions of years they thrived, dominating the landscapes of the Jurassic in ways no other land animals have ever done. Their fossils, found on every continent, testify to just how successful they were. From North America to Africa to Asia, sauropods left their mark in bones, teeth, and footprints. Their dominance didn't mean exclusion of other herbivores. Stegosaurs, smaller ornithopods, and other plant-eating dinosaurs shared the land with them, feeding on different plants or using different strategies. The ecosystems were complex with multiple layers of herbivory and predation. But sauropods held the top positions simply because of their size and numbers. They were the rulers of the land, not through aggression or predation, but through the quiet, relentless act of eating, growing, and moving. Even today, when we see their skeletons in museums, the scale is hard to grasp. Standing beneath the neck of a diplodocus, or looking up at the shoulders of a brachiosaurus, you feel the same sense of smallness that any Jurassic animal must have felt. Their bones stretch upward and outward, reminding us that life on Earth has reached sizes beyond anything we can imagine in the present. They challenge our sense of what's possible, and they remind us that ecosystems can support giants when the conditions are right. And those conditions in the Jurassic were exactly right. Warmth, moisture, abundant vegetation, and global stability created a world where sauropods could flourish. They weren't accidents of evolution. They were the natural outcome of an environment that allowed plants to grow endlessly and animals to expand to fill the opportunities that plants provided. The story of sauropods is the story of the Jurassic itself. Enormous, resilient, and constantly shaping the land around them, they were the defining presence of their age, but they weren't alone. and their world was filled with predators, smaller herbivores, and creatures of the skies that made the landscapes even more dynamic. If the sauropods were the rulers of the land through their size and abundance, the predators of the Jurassic were the forces that tested them, shaped their behaviour, and kept the balance of the ecosystem in motion. Among these predators, the allosaurs and their relatives stood out as the dominant hunters of their time. They weren't the only carnivores around, but they were among the largest, most adaptable, and most widespread. When you picture a Jurassic predator stalking across a floodplain or pushing through a fern prairie, chances are you're imagining some form of allosaur. Allosaurus itself is the most famous representative. Fossils of this dinosaur have been found in great numbers, especially in North America, where entire bone beds hold the remains of dozens of individuals. This abundance suggests that allosaurs were not rare specialists. They were common and successful, filling the role of apex predator across vast regions. Adults reached lengths of around 9 to 12 meters, with strong legs, long tails, and powerful jaws lined with serrated teeth. Their skulls were large but relatively light, built with openings that reduced weight while still allowing strength. The teeth were designed for slicing flesh rather than crushing bone, sharp and recurved to tear into prey. What made allosaurs particularly effective was their build. They had strong hind limbs for running and maneuvering, but their bodies were balanced by long tails, giving them speed and agility. Their arms, though smaller than their legs, were not useless. Each hand carried 3 sharp claws which could grip and slash. Combined with their jaws, this gave them multiple weapons to bring down prey. They may not have had the sheer bite force of later predators like Tyrannosaurus, but they didn't need it. Their hunting strategy likely involved slashing bites and coordinated attacks that weakened their targets over time. Evidence from fossil injuries suggests that allosaurs were capable of tackling large prey, including sauropods. Bite marks on sauropod bones match the teeth of allosaurs, showing that they at least fed on these giants, whether by hunting or scavenging. Trackways and bone beds hint at the possibility of group behaviour. While it's debated whether allosaurs truly hunted in coordinated packs, it's possible that they at least tolerated each other around kills, much like modern crocodiles or big cats. In places where prey was abundant, groups of allosaurs may have gathered, taking advantage of opportunities too large for a single individual to handle. Allosaurs were not the only large predators of their age. Their kin included other theropods that filled different niches. Some were smaller and more agile, focusing on swift herbivores rather than massive sauropods. Others grew nearly as large as Allosaurus itself, dominating different regions of the world. Together, they created a landscape where predators came in many sizes, each shaping the behaviour of herbivores in turn. The interactions between predator and prey were constant. Imagine a herd of stegosaurs moving slowly across a floodplain, browsing on ferns. The adults carried their distinctive tail spikes, capable of inflicting deadly wounds. An allosaur circling nearby had to calculate carefully whether the risk was worth the reward. Attacking a healthy adult stegosaur could mean being impaled. The safer option was to target juveniles or injured individuals. This constant push and pull shaped the evolution of both sides. Predators had to be strong, fast, and adaptable. Herbivores had to develop defences, whether in the form of armour, spikes, or group behaviours. Allosaurs were also opportunists. Fossil evidence shows they fed on carcasses as well as live prey. In a world where survival was never guaranteed, ignoring an easy meal would have been a mistake. They could smell or see a fallen dinosaur from a distance, approach carefully, and feed until driven off by competitors. Scavenging didn't make them less effective hunters, it simply made them versatile. The ability to exploit multiple food sources is one of the reasons they thrived for millions of years. Other predators of the Jurassic added to this dynamic. Smaller theropods hunted the understory, preying on mammals, lizards, and young dinosaurs. Some may have been feathered, their bodies covered in simple filaments that offered insulation or display. These smaller hunters were quick and stealthy, filling roles similar to foxes or coyotes today. Mid-sized theropods targeted medium herbivores, while allosaurs and their close relatives focused on the largest prey available. This layering of predator sizes created a balanced ecosystem where every niche was filled. The physical evidence of predation is preserved in surprising ways. Bones of herbivores sometimes carry tooth marks, healed or unhealed, showing that they survived attacks or were consumed after death. Pathologies on predator bones suggest that hunting was dangerous, leading to injuries that sometimes healed poorly. In some cases, bite marks on predator bones match the teeth of other predators, implying fights over food or territory. These fossils remind us that life for Jurassic predators was not easy dominance. It was a constant struggle, full of risks and competition. Allosaurs themselves show evidence of this struggle. Some skeletons have broken bones that healed, suggesting they survived significant injuries. Others have infections that would have weakened them. Living as a predator required not just strength but resilience. Injuries could come from prey fighting back, from rivals, or from accidents while hunting. Yet despite these challenges, allosaurs and their kin continued to thrive across the Jurassic world, adapting to new environments as continents shifted and climates changed. One of the keys to their success was their adaptability. They weren't locked into one prey type or one environment. They could hunt sauropods in forests, stegosaurs on open plains, or smaller herbivores along riverbanks. Their bodies were versatile enough to handle different conditions. This adaptability meant that when ecosystems changed, they could follow prey into new territories rather than disappearing. It also allowed them to spread widely, with relatives found in Europe, Africa and Asia, as well as North America. The presence of these predators influenced every aspect of herbivore behaviour. Herding among sauropods and stegosaurs wasn't just about protecting young from environmental hazards, it was a response to predators. Moving in groups reduced the chances that any single individual would be taken. Defensive adaptations like plates, spikes and armour were sharpened by the constant threat of attack. Even the speed and agility of smaller herbivores can be traced back to the pressures of predator pursuit. Without the allosaurs and their kin, the evolutionary arms race of the Jurassic would have looked very different. When you think of the landscape of the Jurassic, don't picture it as a peaceful parade of giants grazing undisturbed. Picture it as a constant balance, where the shadow of a predator could fall at any time. An allosaur emerging from the edge of a forest would send herds scattering. A young sauropod that strayed too far from its group risked being taken. Even predators had to watch their backs because rivals might challenge them for kills. It was a world in motion, shaped as much by the hunters as by the hunted. And yet, despite the violence inherent in their lives, these predators were not mindless killers. They were animals living by instincts honed through evolution, surviving day to day. They cared for their own survival, their growth, their reproduction. They weren't villains in the story of the Jurassic. They were essential players, maintaining the balance of ecosystems that depended on checks and pressures from every direction. Without them, herbivore populations could have grown unsustainably, leading to collapses. With them, the system maintained a dynamic equilibrium. Allosaurs and their kin left a deep mark on the fossil record, but they also left a mark on the imagination. When you stand in front of an Allosaurus skeleton in a museum, its jaws gaping and claws extended, it's easy to picture the fear it must have inspired. But it's just as important to remember the role it played in shaping its world. It wasn't just a predator. It was part of an intricate web that tied together ferns, cycads, sauropods, stegosaurs, and even the smallest mammals. Every step it took sent ripples through that web, influencing the lives of countless other species. When you picture the skies of the Jurassic, you might imagine them ruled entirely by pterosaurs, with their long wings stretched between elongated fingers, gliding and diving above coastlines. And it's true that pterosaurs were the first vertebrates to master powered flight, filling the skies for tens of millions of years. But the Jurassic was also the moment when another story began to take shape, one that would eventually reshape the skies of the Earth forever. This was the dawn of birds. The earliest birds did not look like the sparrows, crows, or hawks you know today. They were closer to their dinosaur ancestors than to anything modern, and in many ways they straddled the line between two worlds. Archaeopteryx, discovered in the 19th century in the limestone quarries of Germany, remains the most famous of these early birds. Fossils of this creature show a blend of features that puzzled scientists for decades. On the one hand, it had feathers, wings, and a wishbone, features that tie it clearly to birds. On the other hand, it had teeth in its jaws, claws on its wings, and a long bony tail, features that were unmistakably dinosaurian. It was a mosaic, a creature caught in transition, showing how flight evolved from small feathered theropods. Feathers themselves had been around before true birds appeared. Many small theropod dinosaurs carried simple filamentous feathers, which may have first evolved for insulation or display. Over time, these feathers became more complex, branching and forming structures that could catch air. The leap from feathers used for warmth or show to feathers used for flight was gradual, but in the Jurassic it was underway. Archaeopteryx and its relatives were experimenting with the skies, testing what it meant to move through the air not with stretched skin like pterosaurs, but with feathers attached to arms that had become wings. The flight of these early birds was probably clumsy compared to modern species. Their wings were capable of flapping, but their skeletons lacked some of the refinements that give modern birds the efficiency to soar and maneuver with ease. They may have relied on gliding from tree to tree, flapping only in bursts to extend their range or avoid predators. They weren't masters of the sky yet, but they were learning, and in the meantime, feathers gave them advantages beyond flight. They provided insulation, keeping body temperatures stable. They offered opportunities for display with patterns or colours that could attract mates or warn rivals. They even helped camouflage, breaking up outlines against foliage. The discovery of Archaeopteryx fossils was one of the turning points in paleontology. When the first specimen was described in the 1860s, it arrived just as Darwin's theory of evolution was being debated. Here was a fossil that looked like both a reptile and a bird, evidence of transition in stone. Its impact on science cannot be overstated, but in its own time, Archaeopteryx was just one of several small feathered creatures taking advantage of the Jurassic environment. Other feathered theropods likely lived in Asia and elsewhere, though fossils are rare. The limestone quarries of Germany preserved Archaeopteryx because the conditions there were exceptional, turning delicate bones and feathers into impressions that lasted for millions of years. The environments these early birds lived in were complex. Forests of conifers and cycads provided perches. Fern understories gave cover for small prey. Insects buzzed through the air, providing food that could be snatched in mid-flight. Small lizards and mammals scurried below, vulnerable to quick attacks. The sky itself was not safe because pterosaurs dominated it with wingspans ranging from modest to enormous. Early birds had to navigate a world already full of aerial competition, carving out niches where they could survive. One advantage birds had over pterosaurs was their feathers. While pterosaurs relied on membranous wings stretched across long fingers, birds had feathers that could be adjusted individually. This gave them greater control over lift and maneuverability, even if they hadn't perfected it yet. Over millions of years, this advantage would allow birds to diversify into an astonishing array of forms, eventually surpassing pterosaurs in dominance. But in the Jurassic, they were still newcomers, fragile and experimental. The diets of these early birds were varied. Insects were likely their primary food, abundant and accessible in forests and open areas. Some may have fed on small vertebrates, catching lizards or mammals when the opportunity arose. Others may have scavenged, picking at carcasses or feeding on leftovers from larger predators. Their sharp teeth, unlike the beaks of modern birds, allowed them to grip and tear. This versatility in diet gave them resilience, a key factor in their survival and eventual success. Fossils of Archaeopteryx show that it had claws on its wings, a feature that may have allowed it to climb trees. If so, it may have lived much of its life among branches, launching short flights or glides to move between perches. Its long tail, stiffened by bones, would have helped with balance and manoeuvring. In life, it may have looked like a small feathered dinosaur with wings, hopping and gliding rather than soaring gracefully. But that was enough. In the dense forests of the Jurassic, where cover was plentiful and predators were everywhere, even short flights could mean the difference between life and death. The presence of early birds also influenced the behaviour of other animals. Insects faced new aerial hunters, forcing them to adapt. Small mammals that once relied on cover alone now had to watch the skies. Even pterosaurs may have felt the competition, though they were far larger and occupied different niches. The addition of birds to the ecosystem layered new interactions into already complex food webs. It's tempting to think of these first birds as minor players compared to the giants of their world, but their significance lies in what they represented. They were the beginning of a lineage that would outlast almost everything else from the Jurassic. While sauropods, stegosaurs and allosaurs would vanish at the end of the Cretaceous, birds would persist, diversifying into over 10,000 species alive today. The calls of Archaeopteryx may have been crude compared to modern songs, but they were the first notes in a chorus that still fills the planet. The evidence of feathers in the Jurassic has grown stronger with discoveries from China and other regions, where fossils of small theropods show feather-like coverings. Some of these animals were not true birds, but they reveal how widespread feathers had become. They weren't rare accidents. They were part of a broader evolutionary trend. Feathers were proving useful in multiple ways, and birds were one of the results. The line between small feathered dinosaurs and true birds was blurred, making it clear that the transition was gradual, not sudden. Picture a forest clearing in the late Jurassic. A small feathered creature climbs onto a branch, its wings spreading slightly as it balances. Insects flicker in the air, catching the sunlight. With a sudden leap, it flaps awkwardly, gliding downward to another tree. A predator moves in the distance, but the little creature has already vanished into the branches. It isn't graceful, but it survives. Over time, its descendants will refine that leap into flight, turning awkward glides into soaring journeys across continents. But here, in this moment, it's just another animal finding a way to live. The dawn of birds in the Jurassic wasn't about sudden dominance. It was about potential. It was about new possibilities opening up in the skies, about small animals taking advantage of feathers in ways their ancestors never had. It was about survival in a world filled with giants, achieved not by size but by adaptation. And as the Jurassic rolled on, those feathered shadows continued to test the air, their wings carrying them slowly toward a future where they would inherit the skies. When people imagine the Jurassic, they usually think of enormous dinosaurs dominating forests and plains. The scale of the giants is so overwhelming that it's easy to forget that most of the animals sharing that world were not huge at all. They were small, often overlooked, and yet they carried just as much importance for the balance of the ecosystem. Mammals scurrying in the shadows, insects humming through forests, amphibians croaking near streams, and reptiles no bigger than your hand all played their parts. These tiny travellers filled every corner that the giants could not reach, shaping the details of life in ways that were every bit as vital as the sweeping presence of the sauropods. Mammals had already appeared long before the Jurassic began. They were descendants of earlier synapsids, small creatures that branched off from the line that produced reptiles. By the Jurassic, mammals were firmly established, though they looked nothing like the large, varied forms we know today. Most were about the size of a mouse, rat, or shrew, built for speed, agility, and survival in a world where predators could crush them in a single step. Their skeletons show adaptations for quick movement, digging, and climbing. Many were nocturnal, taking advantage of the night when the great dinosaurs were less active. Fossils of early mammals like Morganocodon and Dryolestes reveal details about their lives. Their teeth were already specialised, with molars adapted for chewing food more effectively than reptiles could. This gave them an advantage when feeding on insects, small vertebrates or plants. Mammals had faster metabolisms than reptiles, which required them to eat more often, but it also gave them more energy for activity. Their fur, another important adaptation, provided insulation, allowing them to survive in cooler nights or in shaded understories where temperatures dropped. These features may sound ordinary today, but in the Jurassic they were cutting-edge survival strategies. The mammals of the Jurassic weren't trying to compete with sauropods or stegosaurs. They survived by occupying niches too small for dinosaurs to notice. They hunted insects in the leaf litter, dug burrows for safety, and raised young in hidden nests. Some could climb trees, scurrying through branches in search of food. Others lived along riverbanks, feeding on aquatic invertebrates. Their diversity was already impressive, even though their size remained modest. By avoiding direct competition with larger animals, they carved out safe zones in a dangerous world. Insects were even more widespread, their presence shaping every ecosystem on land. They had been around for hundreds of millions of years already, and by the Jurassic they included beetles, flies, dragonflies, wasps, and many others. Without flowering plants, pollination wasn't yet the major role it would become later, but insects were still crucial as decomposers, predators, and prey. They broke down dead plants and animals, recycling nutrients into the soil. They preyed on each other, forming complex food webs, and most importantly, they provided food for countless other creatures. Birds, mammals, amphibians, reptiles, and even some dinosaurs depended heavily on insects as a primary food source. Imagine the air above a Jurassic wetland. Clouds of dragonflies hovered, their wings beating fast enough to produce a constant shimmer. Some species reached wingspans larger than modern dragonflies, though the absolute giants of the Carboniferous had already disappeared by then. Beetles scuttled across decaying logs, their hard shells protecting them from predators. Ant-like insects built colonies underground, defending their tunnels fiercely. Mosquito-like forms buzzed, feeding on the blood of reptiles or amphibians. Insects were everywhere, filling the silence with a hum that never ended. These insects weren't just background noise, they influenced evolution directly. Small dinosaurs that began experimenting with feathers likely hunted insects, catching them with quick leaps or snaps of jaws. Early birds relied on them as steady prey, snapping them mid-flight. Mammals fed heavily on them, shaping their teeth and hunting behaviours around their capture. The abundance of insects gave smaller animals a reliable food source, one that didn't require bringing down giants or competing for scarce vegetation. Amphibians were also part of this world of small wonders. Frogs had already appeared, their calls echoing near ponds and rivers just as they do today. Salamander-like forms swam through streams, hiding under rocks and feeding on insects and small fish. These amphibians thrived in the humid greenhouse climate, which provided plenty of water for breeding and survival. Their fossils often appear in wetland deposits, showing that they were widespread. While they didn't dominate in numbers like insects or mammals, they played their roles in food webs, feeding predators and consuming invertebrates. Reptiles of small size were also abundant. Lizards scurried across rocks, basking in sunlight and darting after insects. Early relatives of crocodiles lingered near waterways, some fully aquatic and others spending part of their time on land. Turtles paddled in rivers and ponds, their shells offering protection from predators. Snakes had not yet evolved, but other small reptiles filled niches as hunters of insects and small vertebrates. Their presence, like that of mammals and amphibians, added to the layered complexity of the ecosystem. The importance of these tiny travellers becomes clearer when you consider the balance of energy in an ecosystem. Large herbivores consumed vast amounts of plants, but their numbers were limited by the need for so much food. Large predators were even fewer, dependent on the herbivores. But insects, mammals, amphibians, and small reptiles existed in staggering numbers. They recycled nutrients, moved energy upward through food webs, and ensured that no resource went entirely to waste. Without them, the system would have collapsed. The giants depended on the tiny creatures just as much as the tiny creatures depended on the giants, even if indirectly. Fossil sites sometimes preserve these small wonders in incredible detail. The limestone deposits of Germany, famous for Archaeopteryx, also contain insects with wings and bodies so well preserved that researchers can study their patterns. Burrows in rock layers reveal the behaviour of small mammals or reptiles that dug into the ground. Coprolites, or fossilised droppings, show insect parts within them, confirming diets. Each of these fossils reminds us that the Jurassic wasn't just about giant skeletons, it was about whole communities, from the smallest to the largest. It's easy to imagine how these small animals lived day to day. A mammal leaves its burrow at dusk, its whiskers twitching as it searches for beetles among ferns. It pauses at every sound, aware that predators lurk nearby. A dragonfly flashes past, hunting mosquitoes above a pond. Frogs call out from the water's edge, their voices echoing into the night. A lizard warms itself on a fallen log, then darts down to snap up an ant. Each of these actions is tiny on its own, but together they form the heartbeat of the ecosystem. The survival strategies of these creatures were simple but effective. Stay small, stay hidden, reproduce quickly, and take advantage of abundant food sources. These strategies allowed them to persist in a world where size often determined survival. They didn't need to outgrow the dinosaurs, they just needed to outlast them, and in the long run that's exactly what mammals did. Their small size and adaptability gave them the resilience to survive events that would later wipe out the giants. But in the Jurassic, their story wasn't about future triumphs. It was about daily existence, about scratching out a living in the spaces left open by the massive players of the age. Their lives were no less real or important. They were constant, subtle forces that kept the system working. Without them, the great dinosaurs would not have had the stability to thrive. So while the eye is always drawn to the towering sauropods or the stalking allosaurs, it's worth lowering that gaze. The Jurassic was full of life at every scale, and the tiny travellers mattered just as much as the rulers of the land. They fill the spaces under ferns, inside logs, along rivers, and in the air. They were everywhere, making the world alive in ways that bones and teeth alone cannot capture. If you try to picture the Jurassic, it's easy to focus on what you would see. Towering trees, giant dinosaurs, warm seas, and endless ferns dominate the imagination. But sight was only part of the experience. The world of that time was also full of sound, and if you could stand quietly in a forest, a plain, or on a coastline, you'd hear an environment that was never silent. The soundscape of the Jurassic was as important to life as the plants and animals themselves, because animals relied on sound for communication, for warning, for hunting, and for survival. The mix of noises carried across forests, prairies, wetlands, and seas, creating a constant background that would feel both familiar and alien to modern ears. Start with the forest. Under conifers stretching over 100 feet tall, the wind moved through branches, rustling needles with a steady hiss. Cycads and ferns swayed at ground level, adding a softer rustle underneath. Insects buzzed constantly, their wings vibrating in high-pitched tones that rose and fell as they passed. Frogs croaked near streams, filling the lower register with rhythmic calls. Somewhere deeper in the understory, a mammal squeaked briefly as it scurried through the leaf litter. All of these small sounds blended into a living background, a hum of activity that never stopped. Then came the larger voices. Herbivorous dinosaurs communicated with one another across the trees. Sauropods, with their enormous bodies and long necks, likely produced deep, resonant calls. These low-frequency sounds could travel for miles, vibrating through the ground and air alike. Modern elephants use similar infrasound, too deep for humans to hear clearly but strong enough to reach across entire herds. A Brachiosaurus might have lifted its head above the canopy and let out a rumble that echoed for kilometers, letting others know where it was or signalling readiness to move. Diplodocus herds may have exchanged constant low calls to stay coordinated as they travelled. Other herbivores had their own sounds. Stegosaurs may have used deep grunts or low bellows to warn predators or communicate with mates. Their tails, armed with spikes, may have added sound to the landscape when swung against the ground in display. Ornithopods, smaller plant eaters, could have produced higher-pitched calls, chirps, or honks, depending on the structure of their throats and nasal passages. Fossil evidence shows that some dinosaurs had complex nasal cavities, which in later relatives like hadrosaurs were used to produce resonant calls. In the Jurassic, those systems were less developed, but sound was still essential to their behaviour. Predators added their voices too. Allosaurs likely roared, but not in the way movies often depict. Their calls may have been a mix of low growls, guttural bellows, or even hissed warnings. Crocodilians today produce deep rumbles by vibrating air sacs in their throats, and large theropods could have done something similar. The sound of an allosaur advertising its presence or warning arrival might have carried through valleys, shaking smaller animals into silence. At closer range, the snapping of jaws, the thud of feet, and the rustle of foliage as predators moved would have been unmistakable. The soundscape of wetlands added its own layers. Along rivers and lakes, amphibians called at night, insects droned in swarms, and turtles splashed as they entered water. Pterosaurs screeched as they circled overhead, their voices sharp and carrying. Fish splashed occasionally, breaking the surface. Marine reptiles closer to the coasts may have surfaced with hissing breaths before diving again. These wetlands would have been some of the noisiest places, full of overlapping calls from animals active both day and night. Night in the Jurassic had its own distinctive sound. When the larger dinosaurs quieted, insects grew louder, their buzzing filling the air. Frogs took over in choruses, while mammals rustled in underbrush. Owls as we know them didn't exist yet, but early birds and small predatory reptiles may have hunted by night, producing sudden cries when they caught prey. The darkness amplified every noise, because survival depended on paying attention to what was moving nearby. On open plains covered with ferns and cycads, the soundscape carried differently. Without dense forest to absorb them, noises travelled farther. A herd of sauropods moving across such ground would have produced a steady rhythm of heavy footsteps, each one thudding into soil. Their tails may have cracked like whips, producing sharp sounds that startled predators or signalled herd movement. Smaller dinosaurs added quicker, lighter footfalls. The wind swept across the open spaces, carrying the rustle of vegetation and the calls of animals for long distances. This openness made sound an essential tool for communication. Along coastlines, the mix of sea and land sounds blended together. Waves crashed or lapped against shorelines depending on weather and tides. Pterosaurs circled, their sharp calls mixing with the constant rush of water. Marine reptiles surfaced with gasping breaths, sometimes producing low calls underwater to communicate. Birds like Archaeopteryx might have screeched in short bursts as they moved through trees near the shore. Insects swarmed in great numbers, adding their constant hum. This mixture of sea and land noises created a rich and varied acoustic environment. It's worth considering how animals used sound not just to communicate but to survive. Herbivores relied on alarm calls to warn herds of predators. Predators listened for the rustling of prey in ferns or the splash of movement in water. Insects produced mating calls that attracted partners but also risked drawing predators. Every sound carried meaning, and silence could be just as important. When the usual background hum suddenly stopped, it signalled danger. Animals froze, listening, waiting for the source of the threat to reveal itself. Fossil evidence supports the importance of sound. The structure of inner ears in dinosaurs shows sensitivity to low frequencies, suggesting that deep rumbles were part of their communication. The presence of resonating chambers in skulls indicates that sound production was sophisticated, not primitive. Even in animals without specialized structures, the need to signal, warn, or attract mates ensured that sound was a constant. The Jurassic was not a mute world. It was alive with calls, clicks, buzzes, and rumbles. The daily rhythm of sound followed the rhythm of activity. At dawn, insects stirred, birds flapped from branches, and herbivores called to gather herds. As the day warmed, the buzzing of insects grew louder, predators moved, and the forest filled with overlapping noises of feeding, calling, and movement. Afternoon storms added their thunder, rolling across valleys and shaking forest with sudden cracks. Rain hammered leaves, rivers swelled, and for a while water drowned out animal voices. When the storm passed, the calls resumed, often louder in the cooler air. Evening brought a mix of sounds as day-active animals quieted and night-active ones grew bold. It was a cycle that repeated endlessly, changing with the seasons but always returning. Imagine standing in a Jurassic forest clearing. You hear the hiss of wind in conifer needles, the chirps of small reptiles, the hum of insects near your ears. In the distance, a sauropod rumbles, the sound so low it's felt as much as heard. Closer by, a stegosaur bellows, warning a predator. Suddenly the calls fall silent and the forest holds its breath. An allosaur steps into the clearing, its growl vibrating through your chest. The moment it passes, the sounds slowly return. First insects, then birds, then the deeper voices of giants. That layering of noise and silence was the pulse of the Jurassic. The soundscape wasn't just about noise, it was about information. Animals used it to make decisions, to find food, to avoid danger, and to choose mates. The forests, plains, wetlands, and seas of the Jurassic were full of messages travelling through the air and water, each one vital to the survival of the creatures that made it. The world of that time was constantly talking, and every species had to listen. The Jurassic world was not only shaped by forests, oceans, and animals. Beneath it all, the Earth itself was restless. Volcanoes and tectonic shifts defined the landscapes as much as living things did, and the land animals, plants, and marine life all had to adapt to a planet that was constantly changing. Fire and stone were everywhere in this age, sometimes quiet for centuries, then suddenly roaring to life in eruptions that covered valleys, darkened skies, and reshaped ecosystems. These events weren't rare accidents. They were ongoing features of a world still pulling itself apart from the supercontinent of Pangaea. The breakup of Pangaea created enormous stresses in the Earth's crust. As the land masses split and drifted, rifts opened, pulling continents apart and letting magma rise from deep within the mantle. That magma created volcanic chains and basalt flows that spread for hundreds of kilometres. Lava fields buried forests, rivers and plains, covering them in stone that would last for millions of years. Volcanic gases poured into the atmosphere, adding to the greenhouse climate that made the Jurassic so warm. The Earth itself was breathing fire, and every creature alive at the time had to live with that reality. Imagine standing near one of these rift valleys. At first, the ground might tremble slightly, shaking trees and sending animals running. Then, a crack opens, glowing with molten rock as magma pushes upward. In hours or days, the eruption grows, fountains of lava rising high, rivers of glowing orange flowing downhill, igniting vegetation. Ash clouds spread upward, blocking the sun, turning day into twilight. For miles around, the world changes in an instant. Animals scatter, rivers boil, forests vanish. And yet, as destructive as these eruptions were, they also created new land, new soils, and new opportunities for life. The Central Atlantic Magmatic Province, which began forming near the end of the Triassic and continued into the Jurassic, was one of the largest volcanic events in Earth's history. It produced vast outpourings of basalt, covering areas that would eventually become parts of North America, South America, Africa, and Europe. These flows altered climates globally, pumping carbon dioxide into the air and driving shifts in ecosystems. They left behind geological formations that we can still see today, reminders of how massive the Earth's volcanic forces were at that time. But not all volcanic activity was so catastrophic. Many volcanoes erupted more quietly, spilling lava gradually or releasing ash that fertilized surrounding soils. Plants often returned quickly after eruptions, with ferns being among the first to recolonize scorched ground. These fast-growing pioneers stabilized soils and paved the way for cycads and conifers to follow. Within decades, areas destroyed by fire could turn green again, transformed into new forests rooted in nutrient-rich volcanic soils. The cycle of destruction and renewal was constant, a rhythm of the land as familiar to Jurassic life as rain or storms. Earthquakes were part of this dynamic too. As tectonic plates shifted, they produced sudden jolts that cracked the land, altered rivers, and triggered landslides. Herds of dinosaurs may have felt the ground shake beneath them, scattering instinctively even before they understood what had caused it. Entire sections of coastline may have shifted during seismic events, changing habitats overnight. In places where rifting was strongest, earthquakes could be frequent, making the land itself feel unstable to the creatures that lived there. Volcanoes also influenced the atmosphere and climate in subtle ways. While eruptions released carbon dioxide and other greenhouse gases that warmed the Earth, they also produced ash and sulfur dioxide that could block sunlight temporarily. This meant that after an eruption, local or even global temperatures might drop for months or years. Plants struggled in reduced sunlight, animals faced lean times, and ecosystems had to adapt to sudden scarcity. Fossil evidence suggests that some disruptions in Jurassic life coincided with pulses of volcanic activity, showing how closely biology and geology were linked. Marine environments were affected too. Ash falling into the sea changed water chemistry, sometimes making it more acidic or reducing oxygen levels. Lava flows entering shallow seas boiled water and killed marine life instantly. But over time, these same processes created new coastlines and underwater platforms where reefs could grow. The Tethys Ocean in particular was shaped by constant geological activity, its coastlines redrawn again and again by volcanic forces. Life adapted by shifting, migrating, or evolving new strategies, always responding to the changes beneath its feet and fins. The sound and sight of Jurassic volcanoes must have been unforgettable. The roar of eruptions carried for miles, rumbling through the ground. Ash fell like snow, coating ferns and cycads in grey layers. Lightning often sparked within ash clouds, crackling across dark skies. At night, the glow of lava could turn entire horizons red. Animals responded instinctively, moving away from danger if they could. Some were caught, their remains preserved in layers of ash and lava that hardened into stone. These fossils give us direct evidence of the link between life and volcanic activity, showing how sudden geological events froze moments of the past in incredible detail. Volcanoes also played a role in long-term planetary processes. By releasing gases, they influenced the global carbon cycle. By building new land, they altered the shape of continents and seaways. By creating fertile soils, they helped sustain vegetation that supported herbivores, which in turn supported predators. This cycle was destructive in the short term, but creative in the long term. Without volcanic activity, the landscapes of the Jurassic would not have looked the way they did, and the animals would not have had the habitats that sustained them. It's important to remember that not all volcanic regions were deadly wastelands. Many were thriving ecosystems between eruptions. Streams ran across cooled lava, forests grew on volcanic slopes, and animals moved through valleys bordered by dormant cones. To the dinosaurs and other creatures living there, these were simply parts of their world, no more threatening in daily life than storms or predators. Only during eruptions did the danger become immediate. For the rest of the time, life carried on, shaping itself around the presence of fire and stone without hesitation. In some regions, volcanic landscapes became permanent fixtures of dinosaur movement. Herds of sauropods may have travelled across plains shaped by lava flows, feeding on vegetation that grew in volcanic soils. Predators followed them, leaving trackways that we can still find today preserved in hardened ash. Rivers carve through volcanic rock, creating canyons and fertile floodplains. Over time, these features became as much a part of the environment as the plants and animals themselves. The interplay between volcanoes and shifting continents never stopped. The movement of tectonic plates created mountains and valleys, opening new habitats while closing others. The rising and falling of land altered rainfall patterns, redirected rivers, and changed the spread of vegetation. Dinosaurs, mammals, insects, and amphibians all had to adapt constantly to these changes. Some species vanished, others thrived. But the dynamic Earth kept driving evolution forward. Picture a Jurassic Valley just after an eruption. Ash blankets the ground, muffling sound. A few charred trees stand black against the sky. But already, green shoots are pushing up through the grey, ferns reclaiming the land. Small mammals emerge cautiously, insects return, and before long, herds of dinosaurs move back into the area. What looked like destruction has become opportunity. This was the rhythm of the Jurassic world. The Jurassic world was a greenhouse planet. There were no polar ice caps, no frozen tundras, and no glaciers creeping across continents. Instead, warmth extended from the equator toward the poles, creating conditions that allowed vegetation and animals to spread across regions that today are frozen and barren. But a world without ice did not mean a world without seasons, and it did not mean a world without storms. The climate was dynamic, driven by shifting currents, powerful rainfall, and weather systems that shaped the daily lives of every creature. The absence of permanent ice meant that sea levels were higher, flooding coastlines and creating wide, shallow seas. These seas absorbed heat from the sun, distributing it through currents that carried warmth across the planet. The result was a climate more uniform than today, with smaller differences between equatorial and polar regions. But even with this general warmth, local variations were significant. Mountain ranges created rain shadows, blocking moisture and leaving deserts behind them. Coastal regions were lush, while inland areas were more arid. Rainfall was abundant in some places and scarce in others. Seasons were still present, though they looked different than the ones you know. Instead of ice and snow defining winter, seasons were marked more by changes in rainfall and storms. Monsoon-like cycles occurred in some regions where months of heavy rain were followed by months of dryness. These wet and dry cycles had profound effects on plants and animals. Ferns and cycads flourished during rainy periods, spreading quickly across floodplains. During drier months, vegetation became scarcer, forcing herbivores to travel farther or feed on tougher plants. Herd migrations may have followed these seasonal rhythms, with sauropods moving across valleys and plains in search of the next flush of growth. Storms were powerful features of this climate. Warm seas fueled massive systems, similar to the hurricanes and cyclones of today, but likely more frequent in some regions due to higher global temperatures. These storms brought torrential rains, high winds, and coastal flooding. Forests could be flattened, river systems swollen, and coastlines reshaped in a matter of days. Dinosaurs and other animals living in storm-prone areas had to adapt by moving to higher ground, seeking shelter in forests, or simply enduring the chaos. For smaller animals, burrows provided protection. For larger ones, survival depended on mobility and resilience. The constant cycle of storms and rainfall influenced the structure of ecosystems. Wetlands formed in low-lying areas, providing habitats for amphibians, reptiles, and insects. Floodplains became fertile zones, enriched by sediments carried by rivers during seasonal floods. Forests regrew rapidly after storms, taking advantage of disturbed ground and increased nutrients. Fire also played a role because lightning from storms often ignited vegetation. These fires cleared old growth, making space for new plants. The interaction of storms, floods and fires created a mosaic of habitats, each at a different stage of regrowth, which supported diverse communities of animals. Evidence of this weather is found in rock layers. Sedimentary deposits show repeated cycles of flooding and drying, with mud cracks, ripple marks, and layers of sand left by shifting rivers. Fossilized soils reveal patterns of seasonal wetness and dryness. In some places, growth rings in fossilized wood show variations that correspond to seasonal changes. Together, these clues tell us that the Jurassic climate was not static, even if it was generally warm. It pulsed with cycles of rain, storm and sun that animals had to navigate. The absence of ice also influenced ocean circulation. Without cold, dense water sinking at the poles, currents flowed differently than they do today. Warm water extended farther, reducing temperature gradients. This helped stabilize climates, but also concentrated storms in certain regions. The Tethys Ocean, with its warm, shallow waters, was particularly prone to seasonal changes, producing monsoon-like rains along its coasts. Animals living near these shores would have been accustomed to rhythms of flooding and retreat, their lives tied closely to the moods of the sea. Imagine a herd of sauropods in such a world. During the wet season, they grazed on lush vegetation, moving slowly through forests and across floodplains, their massive bodies surrounded by green abundance. But as the rains ended and the dry season began, the ground cracked, rivers shrank, and plants withered. The herd had to travel, covering vast distances to find food. Their deep calls carried across valleys as they moved, coordinating migrations. Predators followed, knowing that weakened individuals might fall behind. The entire rhythm of their lives was bound to the cycles of rain and dryness. Smaller animals adapted in different ways. Mammals stayed in burrows during storms, emerging when the rains passed to feed on insects drawn out by wet conditions. Insects themselves timed life cycles to match seasons, emerging in swarms during the wet months when resources were plentiful. Amphibians bred in temporary pools left by floods, their tadpoles racing to mature before the water dried. Reptiles basked when the skies cleared, storing energy for leaner times. Each strategy reflected the demands of a climate without snow, but full of seasonal extremes. Volcanic eruptions added to this complexity. When volcanoes released ash into the atmosphere, weather patterns could shift temporarily. Ash clouds blocked sunlight, cooling areas for months or years. Rain mixed with ash to create acidic conditions that challenged plants. Yet once the skies cleared, the cycle resumed, and storms carried nutrients back into soils. The resilience of Jurassic ecosystems meant that even after major disruptions, life bounced back quickly, often in slightly altered forms that reflected the changes around them. The constant warmth also influenced reproduction and growth. Many reptiles depended on temperature to regulate body heat and egg development. In a warm, stable world, eggs could be laid in a wider range of environments without freezing. Dinosaurs nested in sandy banks, forest clearings, or floodplain soils, their eggs warmed by the sun or by rotting vegetation. Insects multiplied rapidly in warm conditions, supporting food webs. Plants grew year-round in many places, though their productivity still varied with rainfall. This consistency of warmth allowed life to flourish on scales impossible in colder climates. It's worth noting that while there was no permanent ice, local extremes still existed. Some high-altitude regions may have experienced frost, and storms could bring sudden drops in temperature. Animals adapted to these shifts, just as they adapted to drought and flood. The key feature of the Jurassic climate was not uniform comfort, but dynamic stability. Warmth was constant, but the way that warmth interacted with rain, storms, and landscapes created endless variation. Picture standing in a Jurassic forest as a storm approaches. The air grows heavy, insects fall silent, and leaves rustle with the first gusts of wind. Then rain begins, first as a patter, then as a roar, drenching everything. Thunder rolls, lightning cracks, and rivers swell with sudden force. Dinosaurs move through the downpour, their calls barely audible above the storm. Hours later, the sky's clear, steam rises from wet ground, and the forest hums with life again. That cycle repeated countless times, shaping every plant and animal in the world. The sound of rain, the smell of wet vegetation, the rumble of thunder, the rush of swollen rivers, all of these were constants of the Jurassic experience. They defined how animals fed, bred, and survived. A world without ice was not a world without challenge. It was a world where water, warmth, and storms worked together to create conditions both abundant and demanding. The Jurassic was not just a world of giants moving across forests and seas. It was also a time when evolution seemed to test idea after idea, running experiments with body plans, behaviours, and survival strategies. Some of these experiments became the foundation for lineages that are still with us today. Others were dead ends, fascinating but temporary, lasting for a few million years before disappearing. Taken together, they reveal a planet constantly reshaping its cast of life, filling niches, and then trying new solutions when conditions shifted. Dinosaurs themselves were already diverse by this point. Sauropods stretched into some of the largest land animals ever known. Stegosaurs carried bony plates along their backs and spiked tails for defense. Ornithopods were smaller, but agile, with beaks adapted for grazing plants close to the ground. Each of these groups was part of the evolutionary workshop, exploring different ways to feed, defend, and survive. The differences in their teeth, jaws, and limbs show how evolution responded to the availability of plants and the pressure of predators. Where one group grew larger to deter attackers, another grew armour. Where one stretched its neck to reach high vegetation, another developed speed to escape danger. Predators too experimented with form. Allosaurs grew into apex hunters with skulls designed for slashing bites. Relatives of varying sizes filled secondary predator roles, some relying on speed, others on stealth. The fossil record shows a wide range of theropods during this time, some as small as chickens, others rivaling Allosaurus itself. In their bones we can see the beginnings of traits that would one day define birds: lighter skeletons, flexible wrists, and feathers. These adaptations didn't all evolve for flight at first. Feathers may have provided insulation, display, or balance. Only later were they co-opted into wings that carried animals into the air. The first true birds were part of this broader experimentation. Archaeopteryx was one of several forms testing the possibilities of feathered flight. Its claws, teeth, and long tail made it different from modern birds, but its wings show that it was already moving beyond gliding into powered flight. This transition didn't happen in one step. It was the product of countless small changes, each building on the last. Some experiments failed, producing creatures that couldn't compete with pterosaurs or other dinosaurs. Others succeeded, laying the groundwork for one of the most successful lineages in Earth's history. In the oceans, the evolutionary workshop was equally busy. Ichthyosaurs refined their dolphin-like bodies, some developing huge eyes for hunting in deep waters, others growing to enormous sizes. Plesiosaurs split into long-necked and short-necked forms, one specialising in snatching small fish with rapid strikes, the other in crushing larger prey with massive jaws. Ammonites produced endless variations of shells, coiling in tight spirals, stretching into eccentric shapes, or developing ridges and spines. These differences may have been defences against predators, or adaptations to different depths and currents. Their sheer abundance shows how successful these experiments were, even if no ammonites survive today. Reefs were home to their own evolutionary trials. Corals, sponges, and algae built partnerships that created entire ecosystems. Crustaceans evolved stronger claws, better suited to cracking shells or scraping surfaces. Fish diversified into more specialised forms, some built for speed in open water, others shaped for manoeuvring within coral branches. Sharks tried out different teeth designs, from narrow spikes to broad serrations, testing which worked best for the prey around them. The reefs were crowded arenas of competition, and the variety of fossils preserved in them demonstrates just how many strategies life explored. Even plants were experimenting. Conifers dominated forests with towering trunks and needles, but cycads tested different shapes and sizes, some small and shrub-like, others resembling palms. Ferns spread across the ground in endless mats, while horsetails grew tall in wetlands. These groups may not have produced flowers yet, but their cones, spores and seeds represented different solutions to reproduction. Some relied on wind, others on water, and some even on early insects. The Jurassic greenhouse climate encouraged growth on massive scales, but it also tested which plants could survive fire, drought and floods. Those that succeeded spread widely, leaving fossilized forests and coal deposits as proof of their dominance. The smaller animals of the Jurassic also reveal experiments in survival. Mammals tested nocturnality, burrowing, climbing and even gliding. Some early forms may have stretched skin between their limbs to glide between trees, long before flying squirrels appeared. Their teeth show specialization, with some adapted for insect eating, others for omnivory. Amphibians adjusted to new wetlands, while lizards and turtles diversified into forms that filled different niches. Each of these groups carried forward traits that would prove useful later, even if many individual species disappeared. What makes the Jurassic so striking is not just the presence of these experiments, but the scale at which they occurred. With continents breaking apart, climates shifting, and ecosystems constantly disturbed by volcanoes and storms, life was under constant pressure to adapt. Opportunities were everywhere, but so were challenges. Those conditions encouraged variation. Every new niche created by a rift valley, a shallow sea, or a volcanic slope became a place where evolution could test another strategy. Most of those strategies didn't last, but the ones that did changed the course of life on Earth. Some of the experiments seem strange to us now. Ammonites developed shells with wild, irregular coils that look almost ornamental, but those shapes may have helped them float differently in the water or deter predators. Certain stegosaurs carried not just plates, but spikes along their shoulders, extra defences that may have made them harder to attack. Some pterosaurs developed unusual crests on their heads, which could have been for display, species recognition, or aerodynamic balance. These features remind us that evolution isn't always straightforward. Sometimes it produces oddities, and sometimes those oddities become the key to survival. The evidence for all this experimentation is preserved in fossils. Quarries reveal layer after layer of different forms, showing turnovers as species appeared, thrived, and then vanished. Bone beds show sudden die-offs, while other sites reveal long periods of stability. When paleontologists compare these layers, they can trace how experiments overlapped, how one group's rise coincided with another's decline, and how diversity surged in response to environmental change. The Jurassic was not a static age. It was a period of constant testing, where success and failure were written into stone. For the animals living then, of course, there was no sense of being part of an experiment. A small mammal hiding in its burrow was simply trying to survive another day. A sauropod stretching its neck to strip needles from a conifer was simply feeding. An allosaur chasing prey across a floodplain was simply hunting. But taken together, their lives represented the outcomes of millions of years of trial and error, each generation building on the last, each adaptation tested against the realities of the world. If you try to imagine standing in that world, what would strike you is not just the size of the giants, but the variety of everything around them. No two forests were exactly the same. No two coastlines held identical reefs. No two valleys echoed with the same mix of calls. Every region was slightly different because evolution had been working on it, testing new life forms, shaping them to fit the local conditions, and if one form failed, another quickly took its place. The the Jurassic deserves its reputation as one of Earth's great ages of life, not only because of the abundance of animals and plants, but because of the constant creativity at work. It was a time when the Earth itself was an active laboratory, reshaping continents and climates while life responded with endless new forms. Some of those forms were fleeting, others became foundations for the future, but together they made the Jurassic a workshop of evolution unlike any other. Survival in the Jurassic was not guaranteed for any creature, no matter its size. Every day was shaped by the push and pull between predator and prey, by the constant search for food, and by the need to avoid becoming food in turn. This balance defined the age, creating ecosystems that were both stable and dynamic, where each species depended on the presence of others, and where no advantage lasted forever. The rules of survival were written not in words but in movement, in teeth, in armour, in herd behaviour, and in instincts that determined whether an animal lived long enough to reproduce. For the giant sauropods, survival meant feeding almost constantly. Their enormous bodies required hundreds of pounds of vegetation each day, and their necks, tails, and digestive systems were all adapted to help them meet that demand. But eating that much meant they had to move across large areas, stripping vegetation before shifting to new ground. This movement shaped entire landscapes, and it also exposed them to predators. An adult sauropod was nearly untouchable, but the young were not. Herds formed partly to protect juveniles, with adults circling around them when danger approached. The survival of the next generation depended on this constant vigilance. Stegosaurs had a different strategy. They couldn't outgrow predators the way sauropods did, but they could defend themselves with armour and weapons. Plates along their backs may have helped regulate body heat or signal to other members of their kind, but their tails were unmistakably defensive. The spikes, known as the thagomizer, could swing with deadly force, and fossil evidence shows puncture wounds in predator bones that match these weapons. Survival for stegosaurs meant standing ground when necessary, keeping predators wary of an attack that could be fatal. But armour and spikes weren't enough on their own. Stegosaurs still had to feed on low vegetation, stay in groups for protection, and remain alert to threats. Ornithopods and smaller herbivores relied more on speed and agility. With lighter bodies, they could dash into cover or flee across open ground, avoiding predators before they could get close. Some had sharp senses, able to detect danger quickly. Their beaks allowed them to feed efficiently on plants others ignored, reducing competition. But survival came with risks. A moment of hesitation, a stumble in the wrong terrain, or separation from the group could mean death. The balance for these animals was in constant motion. Survival measured in seconds when predators struck. Predators, for their part, faced challenges just as serious. Allosaurs and their kin were apex hunters, but they couldn't simply attack anything they wanted. A full-grown sauropod could crush or kill them. A stegosaur's tail could impale them. Even smaller herbivores in groups could trample a predator if they panicked in unison. Hunting required timing, strategy, and luck. Fossil evidence of injuries on predator skeletons shows that many paid the price for failed attempts. Broken ribs, bitten limbs, and infections were common. For predators, the balance was between risk and reward. They had to eat to survive, but each hunt could mean death or crippling injury. Some predators turned to scavenging when possible. A carcass left behind by flood, disease, or another predator was a valuable resource. Scavenging reduced risk but came with competition. Multiple predators might converge on the same kill, leading to fights. Smaller scavengers like mammals, insects, and small theropods darted in to take their share, while larger ones tried to dominate. Survival in these moments was about hierarchy, with size, aggression, and numbers determining who ate and who went hungry. Insects played their part in survival too. Swarms of them consumed carrion quickly, leaving bones picked clean in days. They broke down waste, recycled nutrients, and spread spores and seeds. For small animals like mammals, insects were a primary food source. For larger ones, they were irritants, biting and feeding on blood. Survival sometimes meant enduring clouds of mosquitoes or avoiding areas thick with stinging insects. The smallest creatures were as much a factor in balance as the largest. The seas of the Jurassic had their own version of this balance. Ichthyosaurs hunted fish and squid, using speed and vision to survive. Plesiosaurs with long necks struck quickly into schools of prey, while pliosaurs dominated as apex predators capable of taking almost anything. Fish darted in schools using numbers as protection, while ammonites relied on shells and mobility. Sharks adapted teeth for different diets, some piercing, some slicing, each testing a different strategy. Just as on land, every advantage was temporary. Survival depended on constant awareness and adaptation. Weather added another layer. Storms could scatter herds, flood nesting grounds, or wash carcasses downstream. Animals had to adapt not only to each other, but to the unpredictability of the environment. A predator might starve during a season of drought when herbivores moved far away. A herbivore might lose its young to flooding. A small mammal might survive a storm only by staying in its burrow for days. Survival wasn't just predator versus prey. It was life versus the forces of Earth itself. The fossil record gives glimpses of this struggle. Trackways show predator and prey side by side, frozen in time as they moved across mud. Bone beds reveal herds that perished together, perhaps caught in floods or trapped by drought. Skeletons with healed wounds show survivors who endured attacks and lived on. Others show fatal injuries, the cost of risk in a world where every decision mattered. Each fossil is a piece of evidence in the story of balance, a reminder that survival was never easy. Even social behaviour was shaped by this balance. Herding in sauropods and stegosaurs reduced the risk of predation. Group hunting, or at least group feeding, may have helped allosaurs dominate larger prey. Communication through sound, sight or movement helped coordinate responses. A herd that moved together could overwhelm a predator's strategy. A predator that learned to isolate individuals could tip the balance the other way. Every behaviour was part of the equation, refined by millions of years of pressure. If you imagine yourself in that world, you'd see survival everywhere. A mammal scurrying from its burrow at dusk, whiskers twitching as it searches for insects. A dragonfly hovering above a pond, vulnerable to a sudden snap from a small reptile. A herd of sauropods moving steadily across a plain, their young kept in the middle. An allosaur watching from a ridge, weighing whether to risk an attack. A plesiosaur gliding through water, neck weaving as it scans for prey. Each scene is survival in motion, predator and prey locked in constant tension. What makes the Jurassic stand out is how stable this balance was over millions of years. New species appeared, others disappeared, but the overall structure of predator and prey remained. Plants supported herbivores, herbivores supported predators, scavengers recycled the rest, and decomposers completed the cycle. Storms, volcanoes, and shifting continents disrupted the balance at times, but life always re-established it. The balance was never perfect, never without cost, but it was persistent. It kept ecosystems functioning, allowing the giants of the Jurassic to thrive alongside the smallest creatures. Survival in this age wasn't about dominance or control. It was about constant adjustment. Every creature, from the smallest insect to the largest sauropod, lived by rules they could never escape. Find food, avoid danger, reproduce, and pass on traits that might give the next generation a chance. That was the balance of the Jurassic, and it's the same balance that continues on Earth today, written in different forms but with the same unbreakable logic. When we think about the Jurassic, almost everything we know comes from the traces left in stone. The animals, plants, and even the landscapes themselves are long gone, but their remains and impressions were preserved in ways that let us reconstruct their world. Fossils are not just bones displayed in museums, they are records of life, death, behaviour, and environment. Each one is a data point in a story written across millions of years, and together they let us see how the Earth looked and how its creatures lived during this age. The most recognisable fossils are the bones of dinosaurs, often massive and dramatic. Sauropod skeletons stretch across museum halls, their necks arching overhead and tails sweeping behind. Allosaur skulls grin with serrated teeth, while stegosaurs show the armour and spikes that once defended them. These skeletons don't just tell us about size and shape. They reveal posture, muscle attachments, and even how animals moved. By studying the joints, paleontologists can reconstruct walking speeds, feeding behaviours, and potential range of motion. The bones themselves are maps of the lives they once supported. But fossils go far beyond bones. Trackways, the preserved footprints of dinosaurs, are equally valuable. When a herd of sauropods crossed a floodplain, their weight pressed deep impressions into mud. When that mud dried and hardened, it captured their steps. Millions of years later, we can see those tracks, sometimes stretching for hundreds of meters. They reveal not just that sauropods were there, but how they moved. Parallel lines suggest herds walking together. Differences in stride length show adults and juveniles side by side. Occasionally predator tracks intersect with herbivore tracks, hinting at a hunt. These frozen paths are snapshots of behaviour, more dynamic than bones alone can provide. Fossilised nests and eggs are another window. Dinosaurs laid eggs in sandy banks, floodplains or forest clearings, and in some cases the nests were preserved. Eggshell fragments reveal details of structure and composition. Entire clutches have been found, sometimes with embryos inside. These discoveries tell us about reproduction, growth, and parental strategies. Some nests suggest that dinosaurs return to the same sites year after year. Others show evidence of communal nesting, with multiple individuals laying eggs in the same area. These fossils remind us that dinosaurs were not just skeletons, but living animals with life cycles as complex as any modern species. Plants left their marks too. Impressions of ferns, cycads, and conifers are common in Jurassic rock. Their fronds, cones, and leaves pressed into mud and silt, leaving delicate outlines that hardened into stone. Some are so detailed that veins in leaves are still visible. These fossils give us direct evidence of the vegetation that supported herbivores. They show how plants were distributed across environments, how forests were structured, and how prairies and wetlands looked. Coal deposits from Jurassic plants also reveal how much vegetation grew and decomposed, storing carbon that shaped the atmosphere. Insects, though small, appear in some fossil deposits with remarkable clarity. The fine limestone layers of places like Germany preserve wings, bodies, and even antennae. Beetles, dragonflies, and flies look almost modern in their details. These fossils help us understand the role of insects in Jurassic ecosystems, showing what species existed and how they might have interacted with plants and animals. Sometimes even the delicate traces of their activities are preserved, such as burrows in wood or feeding marks on leaves. These are the smallest fossils, but they fill in essential details of the picture. Marine fossils are equally rich. Ammonites are among the most abundant. They're coiled shells found in deposits worldwide. They evolved rapidly and spread widely, which makes them excellent index fossils for dating rock layers. Their shells often show complex suture patterns, the lines where the chamber walls met the outer shell. These patterns are so intricate that they almost look decorative, but they were functional, strengthening the shell and helping with buoyancy. Fossil beds filled with ammonites show how numerous they were and how central they were to marine food chains. Other marine fossils include fish skeletons preserved with scales and fins intact. Some even contain stomach contents showing what they ate. Ichthyosaurs and plesiosaurs appear in fossil form too, sometimes nearly complete. One famous ichthyosaur fossil shows a mother giving birth, with a baby halfway emerged, frozen in the act. This single fossil proved that ichthyosaurs gave live birth rather than laying eggs, changing how we understood their biology. Plesiosaurs are often found in marine sediments. their long necks and flippers preserved in positions that suggest how they swam. These fossils bring the oceans of the Jurassic back to life in vivid detail. Coprolites, or fossilized droppings, may not be as glamorous as skeletons, but they are just as important. They reveal what animals ate, often containing plant fragments, bone shards, or insect parts. By studying coprolites, paleontologists can connect predators to prey and herbivores to specific plants. They provide direct evidence of diet that bones alone cannot. In some cases, coprolites are large enough to suggest they came from sauropods, giving us a sense of the sheer volume of food processed daily by these giants. Fossilized burrows and traces of movement are another category. Small mammals or reptiles digging into soil left tunnels that hardened over time. Worms and other invertebrates left trails in sediment that later turned to stone. These ichnofossils, or trace fossils, show activity rather than anatomy, but they are just as revealing. They demonstrate how animals interacted with their environments, where they lived, and how they behaved. Volcanic ash layers sometimes preserve fossils in exquisite detail. When eruptions buried animals or plants quickly, they sealed them off from decay. In some cases, entire communities were preserved together. These ash beds are time capsules, freezing a moment in the Jurassic for us to study millions of years later. They can contain everything from insects and plants to dinosaurs and marine reptiles, all in the same deposit, giving a snapshot of the ecosystem as it was. Fossils also tell us about injuries, diseases, and survival. Bones with healed fractures show that animals could survive serious injuries. Infections appear as changes in bone texture. Arthritis is visible in joints. Predators sometimes have broken teeth, evidence of struggles with prey. Herbivores carry scars from attacks they survived. These details remind us that life in the Jurassic was not just about growth and reproduction. It was also about endurance, pain, and healing. Not all fossils are dramatic or complete. Many are fragments, a single tooth, a partial limb, a shell broken in half. But even these fragments are valuable. A tooth can reveal what animal it came from and what it ate. A shell fragment can date a layer of rock. A bone shard can hint at a predator-prey interaction. Fossils accumulate piece by piece, and paleontologists assemble them into broader pictures of ecosystems and timelines. The very process of fossilization is part of the story. Most living things never become fossils. They decay, are eaten, or are destroyed by weather and erosion. For fossilization to occur, conditions must be just right. Rapid burial in mud, ash, or sand helps protect remains from scavengers and decay. Over time, minerals replace organic material, turning bone or shell into stone. Sometimes impressions remain instead, like leaves pressed into silt. The rarity of fossilization means that each discovery is precious, representing a small chance that life left behind a permanent record. Despite this rarity, fossils of the Jurassic are found on every continent. In North America, formations like the Morrison preserve rich assemblages of dinosaurs, plants, and trackways. In Europe, limestone quarries preserve delicate fossils like Archaeopteryx and insects. In China, fine sediments have revealed feathered dinosaurs and early mammals. In Africa and South America, sauropods and other giants left their remains in vast deposits. These discoveries are global, showing that the story of the Jurassic was not limited to one place, but was a worldwide phenomenon. When we look at these fossils today, arranged in museums or studied under microscopes, they are more than objects. They are connections to a world that no human ever saw, but that shaped the course of life we inherited. Every bone, track, leaf impression, and shell fragment is a piece of evidence that speaks across time. They tell us that the Jurassic was not an abstract age of giants, but a real living world full of complexity. The stone carries those voices forward, letting us listen if we pay attention. You've now walked through forests of conifers taller than buildings, stood among prairies of ferns stretching toward the horizon, dived into oceans where ichthyosaurs darted after schools of fish, and lifted your eyes to skies where the first birds tested uncertain wings, while pterosaurs glided effortlessly overhead. You've seen sauropods move in herds like living mountains, stegosaurs swing their spiked tails against predators, and allosaurs weigh the risk of each hunt. You've watched insects hum through wetlands, mammals scurry under ferns, and amphibians croak from shaded pools. And as you've followed each step, you've also felt the ground shake with volcanoes, storms sweep across valleys, and continents slowly split apart. The Jurassic was never static, never silent, never still. It was a world alive in every sense, and the traces left in stone are only fragments of how rich it truly was. But as you drift back toward your own time, the distance between then and now feels both immense and surprisingly small. 200 million years is a stretch so long it defies ordinary imagination, yet the animals and plants of that time still echo in the living things around you. Birds at your window carry the legacy of Archaeopteryx and other feathered dinosaurs. Crocodiles basking in rivers carry body plans already well established during the Jurassic. Insects that buzz in summer air play roles their ancestors played just as reliably when stegosaurs and diplodocuses fed nearby. Even the forests, though changed by flowering plants that evolved later, carry a lineage that stretches back to those ancient conifers and cycads. The Jurassic is not gone, it is folded into the present. Survival then, just as now, was about balance. Herbivores needed to eat enough to grow, but not so much that they destroyed the plants around them entirely. Predators needed to take enough prey to survive, but not so much that populations collapsed. Insects, amphibians, and mammals had to find their corners in the system, exploiting small spaces left by the giants. That balance was imperfect, constantly tested by storms, eruptions, and shifting continents. Yet life endured, adapted, and even thrived. Looking at the world now, the same pattern continues. Ecosystems still depend on that balance, even though the players are different. The rules are the same, written into the fabric of life itself. Fossils are the voices that speak across the gulf of time, and the fact that we can hold them in our hands or walk among them in museum halls is a reminder of how connected we are to that distant world. A single tooth carries the story of a predator's life. A footprint pressed into mud carries the story of a herd on the move. A fern leaf preserved in stone carries the story of photosynthesis, millions of years before humans even existed. Each fossil tells us that the world has been alive far longer than we've been here to see it, and each fossil also reminds us that extinction is part of that story. Many of the animals you've met across this journey no longer walk the earth. Their disappearance was not always sudden or catastrophic. Sometimes it was gradual, the slow fade of a lineage replaced by another. Other times it was rapid, the product of upheavals in climate or geology. Either way, the history of life is written in both survival and loss. The Jurassic also teaches that resilience is built into the system. After eruptions covered valleys in ash, ferns returned first, followed by cycads and conifers. After storms flooded plains, sediments enriched soils and allowed new growth. After predators struck, herds regrouped, offspring survived, and the balance reset. Even in the face of global change, life kept finding a way forward. That pattern of resilience is one of the most consistent lessons in Earth history. It does not mean life is invincible, but it means that adaptation and renewal are as constant as challenge and disruption. If you think about your own surroundings, you can still see the influence of that ancient balance. Birds in flight are living proof that small feathered dinosaurs took to the skies. Mammals, once tiny insect hunters in the shadows of the Jurassic, are now among the most dominant animals on land. Plants have changed, with flowering species spreading widely in the later Cretaceous, but the foundation laid by Jurassic conifers and cycads remains. Even the continents under your feet carry marks of that time. Rift valleys, mountain ranges and coastlines shaped during the Jurassic still define geography today. The world you inhabit is not separate from that age. It is the result of everything that came before. As you settle back from that journey, picture the rhythm of a single Jurassic day. Morning light filters through tall conifers, insects already buzzing as reptiles bask in the warmth. Herds of sauropods move slowly toward feeding grounds, their calls resonating in low rumbles. Predators stir, scanning for opportunities. By afternoon, storms roll in, drenching forests and swelling rivers, thunder shaking the ground. Evening brings cooling air, frogs and insects rising into choruses. Night settles, mammals emerge cautiously, owls not yet existing but early birds flapping between trees. This rhythm never stopped for millions of years, repeated endlessly until the age gave way to the next. That continuity, that persistence is what fossils capture, and it's what connects you to a world that seems impossibly far away. The closing reflection on the Jurassic is not that it was alien, but that it was real, physical, and full of life. It was a world where survival depended on the same forces that shape existence today: food, water, shelter, reproduction, and adaptation. The animals and plants were different, but the logic was the same. The traces they left in stone allow us to know them, to understand how they lived, and to see that the Earth has always been dynamic, always in motion, always alive with experiments and balances. And now, as you return to your own time, you carry those images with you. Not as distant myths or unreachable curiosities, but as part of the same story you belong to. The Earth you walk on is the Earth they walked on. The skies you see are the skies they tested. The oceans you know are connected to the seas they swam. 200 million years may stretch the imagination, but it does not break the thread. The Jurassic is still here, written into stone, carried into the present by living descendants, and waiting for you to remember it whenever you choose to look back